Hello everybody and welcome to Laser Defender, where we're going to be building a top-down arcade style shooter. Now this project is quite a bit bigger than the ones we've encountered so far, but along the journey we're going to be adding a load of really useful tools to our toolbox. So what sort of things are we going to be learning? Well, we're going to be instantiating or creating objects at runtime, so we're no longer going to be limited by just the things we place in our hierarchy. We're finally going to add music and sound effects to our game to really help bring it to life. And in that same vein, we're also going to be adding particle systems and camera effects to really juice up the feel of our game. Because this is a bigger project, we're also going to be adding more scenes to our game. So we're not just going to be limited to restarting the same level over and over again. Over on the code side, we're going to be introduced to a brand new type of looping structure known as a while loop. We're going to look at the singleton pattern and when this can be useful and when to avoid it. And we're also going to look at coroutines, which are incredibly useful for things like delaying the execution of our code or creating loops outside of our regular update loop. So there's quite a lot to cover. So when you're ready, go ahead and dive right into the first lecture. Okay, you know the drill. Before we jump into Unity and start building our project, it's a good idea to create our game design document. And with Laser Defender, we're going to be making a slightly larger project this time than we have done so far in the course. And so our game design document is going to be slightly more detailed. So let's think about our GDD for Laser Defender. And to start with, let's just cover off the basic concept of this game. First up, it's going to be a space shooter, so we can think of it in terms of the old arcade games like Galaxian and R-Type. The general premise of the game will be to avoid waves of enemies for as long as possible, and to shoot enemies to score points. So it's going to have a really old school arcade vibe to the game. Because our game is slightly larger than before, we're not going to be constrained to a single scene in our project anymore. So the general flow is that our game will start on a main menu screen where we can decide to start the game or quit. From here, once the player clicks on start, we're going to transition into a new scene, which is going to be our core game. And then once the game has finished, once the player has died, we're going to transition into a final scene, which is our game over scene. This scene is going to display our score and give the player the option to either play again, going straight back into our game scene, or loop background to our main menu. So that's going to be the general flow of how the player interacts with our game. But now let's take a closer look at what's going to happen within the game scene itself. So on this screen, there's a little bit going on, so let's break it down. First of all, we're going to need a player that we can control, and we're going to need enemies that we can avoid. For our game, the enemies aren't just going to move around randomly, we're going to get them following a fixed path, and we're also going to get them spawning in waves. Now at this point, we've essentially got a game, we've got a player and some enemies for that player to avoid, but it would be great if we could start shooting at the enemies and they could shoot back at us. So on this screen as well, we have some projectiles. We have the blue projectiles from the player and the orange projectiles from the enemies. We have the remnants of an enemy here with a particle explosion, so we're going to learn all about the particle system for that. And then down at the bottom of the screen, we have the UI, so we have a health slider, and we've seen sliders before. And we've got some score text. So quite a few moving parts there, and we'll come back to that in just a moment. For now though, let's consider the general game design. For the theme, I'm going to make mine a space shooter. So think of a good theme for your particular version of this project. For the player experience, I want the player to feel very frantic. So there's going to be lots of enemies on the screen, bullets flying everywhere, and explosions happening all over the place. But the core mechanic really just comes down to shooting enemies and dodging bullets. So I'm kind of going for that easy to learn, difficult to master kind of gameplay. As for the general game loop, we're just going to have a single level with endless enemy waves spawning. So the player is going to have to shoot the enemies to score points until such a point where their health reaches 0 and the game ends. Now because our game is a little bit bigger than what we're used to so far, it might be a good idea to do a quick feature analysis to see roughly what we want to build. So I like to break down all the proposed features that are going to go into my game to see what's really essential and what's just kind of nice to have. So all of the essential stuff we call the core gameplay. And for this game to really function, we're going to need to have a player that can move. But a player moving on the screen doing nothing isn't really exciting or frantic gameplay, so we're going to add some enemies, and they're also going to have to move. But rather than working out some complicated AI or just having them randomly move around, we're going to have them move and spawn in enemy waves. So the enemy movement and the enemy wave system that we're going to build are very closely related to each other, and we can't really have one without the other. The final piece of core gameplay, in my opinion, will be player health. Because if the player can't die, then the game can't end, and there'll also not be any real stakes or point in playing if the player can't die. So with that, we have a functioning game, and you may be wondering how the player can die in this kind of situation, and we could just make it that when the player collides with an enemy, then they lose health and die. But to make this game a bit more fun and a bit more frantic, we wanted to be able to shoot enemies and dodge bullets. So for our secondary features, the big one is going to be shooting, and you may argue that this should be a core feature for our game. But by adding shooting, we also add some extra mechanics that we need to worry about, and the main one is enemy health. So now that we can shoot back, we need a way of destroying enemies. And then finally, for our secondary features, we're going to want a scoring system, so that the player can see how well they did on their last run. Now, with our core and secondary features all planned out, we do have a working game, but it's very much lacking polish. Polish will generally be added at the end of development, but to keep game development interesting, it is nice to do a little bit of polish here and there as you build your game. So polish for our game will include things like visual effects, so enemies exploding into showers of particles. We'll have some sound effects for when the enemies and the players shoot at each other and explode. We'll have our menus and additional game screens. And finally, our last piece of polish will be extra content and tuning of our variables. So this will be adding additional enemies, additional waves, and generally making it so the game is playable without being too easy or too difficult. Now, with our feature analysis out of the way, we know roughly what we need to build, and also because we've stacked these into individual boxes, we kind of know roughly what type of script we're going to need to create our game. So we might have a player movement script and a shooting script, and so on. So with our feature analysis done, let's finally look at the art assets that we're going to need for our game. And these might come from a pre-created asset pack. You may choose to use the same ones that I'm using, or you may want to create your own. But the ones we're going to need are going to include our player ship, so we're going to need something for the player to move around the screen. We're going to need some enemy ships, and this may be one or more, depending on if you have different types of enemy in your game. Since we're going to have the enemies and players shooting at each other, we're going to need something to act as a projectile. To save us playing against a blank black background, then we're going to want some sort of background sprites, so I'm going to be using a nice star field for my space theme. But again, you can choose whatever works for your particular genre that you've picked. We're going to need some fonts for our score text and for our main menu and end screen. And finally, we're going to need some UI sprites for things like our buttons and any other objects that we want to add to our canvases. So that's our slightly more in-depth GDD for this section. And now it's time for your challenge. I want you to go ahead and choose your theme. So it may be a space theme like mine or something entirely different. I then want you to create your game design document and share your document with the community. So go ahead and complete that challenge, and I'll see you in the next lecture where we go ahead and set up our project. So I'll see you there. In this lecture, we're going to set up our Laser Defender project and also do a little bit of messing around with the Unity editor, because as you can see here, I'm currently in a Unity 3D scene. And that is because when I created this project, I accidentally on purpose clicked on the 3D preset instead of 2D. And the reason I did this is to show you how to get from the 3D state into the 2D state if you don't automatically set 2D when you create your project. Now, to save you some time, you are probably going to be better off just starting up a new project and remembering to set that 2D option. But if you are in a 3D project, then let me walk you through some of the setup we're going to have to do and some of the pitfalls and challenges we're going to face later on in development. So the first step to setting up our project to act like a 2D project is to go over into the hierarchy, and rather than just having a main camera, we've now also got a directional light. We're not going to need this for a 2D game, so we can just really go ahead and delete it. This will leave us with just our main camera, and in here this is set up for 3D as well. So over on our camera component, the first thing we probably want to do is change our projection mode from perspective to orthographic. Finally, we want to remove our skybox and just have a flat background. So we can change our clear flags from skybox to solid color. But in our scene view, we can still see the skybox. So let's have a look at how we get rid of all of this and just work with a plain flat background. Up at the top of our scene view, we have a whole bunch of options. And to get rid of the skybox, we want this little stacked icon with the plus sign above it. And we can either disable all of that entirely, or in the drop down, we have a whole bunch of options where we can select whether we can see our post-processing, our particle effects, and things like that. We will be using particle systems, so let's leave that on, but instead switch off our skybox, our fog, and since we're not going to need it, we might as well turn off our flares as well. Finally, up in this top bar, we also have this 2D button. And if we click on this, it will change our camera and put us into a 2D flat view. Now, back in previous versions of Unity, this is pretty much all you'd really have to do. However, in the more recent versions of Unity, all of the 2D assets and packages have all been wrapped up separately to the 3D environment. So if we were to say, go ahead and right click on our hierarchy, we'll see that we've got 3D objects, but we don't have any 2D objects, so we can't add any sprites to the game. Now to fix this, it's just a case of coming up to our window and then down to our package manager. And if we go ahead and select the Unity registry, right at the very top, we'll have a load of 2D packages that we can choose from. Now, if you've set your project up as 2D already, you'll notice that pretty much all of these are already installed. The only one missing will be the 2D tile map extras. At its most basic, the only one you really need is the 2D sprites. So let's go ahead and install that first. And once that's installed, if we go ahead and right click on the hierarchy now, we'll see that we have our 2D objects. So we can now add the sprites to our scene. And we're not really going to be using any of these other 2D options, but if you want to, go ahead and install these anyway, and then your project will be in exactly the same state as it would have been had you selected the 2D option when creating the project. Now, while we're in the package manager, we may as well go ahead and set up the other packages we're going to need for our project as well to get that out of the way. So let's go down and double check that we've got our Text Mesh Pro installed. And the last package we're going to need, if we scroll up, is going to be the input system, because for this project, we're not going to be using the old inbuilt input system with Unity. We're going to be using their new fancy input system. So let's go ahead and install that as well. Now, during this install process, you will be presented with this warning message, and this will ask you if you want to restart the editor and disable the old Unity Engine inputs. So let's go ahead and click yes, and this will finish off the installation process and then restart Unity. And this might take some time to just re-import everything and reload the editor. So once the editor has reloaded, let's go ahead and close the package manager. And don't worry too much about that input system that we've just brought into our project. We'll get there and we'll look at it in a lot more detail when we start moving our player around the level. Now, the next thing I want to show you in here is how to change your editor around and save new layouts. Because when I'm working on a project, I'm not actually a massive fan of having my hierarchy over on this side of the screen. Because a lot of the time I need to access something in the hierarchy and then do something in the inspector. And we can move and rearrange all these elements on our screen. If we click on the tab at the top that says hierarchy and then just click and drag, so left click and move it around, we'll see that we can move it around to different areas of the screen. So I'm going to drag it to the right of my scene view and snap it into place. And for this particular game, I'm also going to take the game window and just snap it to the left of my scene view so I can see my game and my scene in the same view. Now you can continue to drag and drop different areas of your screen and set up your editor however you like. Once you're done, if you go up to the top right drop down where it says layout, we can go down and save our new layout. Here we can give it a new name and we can really name it whatever we like. I'm just going to call mine the Laser Defender layout or LD layout and hit save. And now if we click on our layout drop down again, we'll see that we've got our LD layout in our list. So if we want to go back to default, we can click on our default option. And if we want to go to our Laser Defender layout that we've created, we can click on that. Okay, so with our layout now set up, I'm actually just going to open this up a little bit more so we can see some of the other options that we've got here. So we can always resize and move however we like. But for now, the only one I really want to see is this free aspect drop down. And that's because we're going to change our aspect ratio for our game. Our space shooter is going to be somewhat mobile friendly. So I'm going to go with a 9:16 aspect ratio. I've already got a pre-created one in my list here. But if you don't have that, then you can just click on the plus button, give it a name, so 9:16, change the type to aspect ratio, and then just specify the width and height that you want. So in this case, it'll be 9 on the X and 16 on the Y. Then if we go ahead and click on our 9:16, we can kind of see why this layout is nice for our game, because we can hide our game window all the way to the side here and still see everything that's going to be going on screen, but then have a nice large workspace for working in the scene itself. Next, for our project setup, we're going to need some assets, and that is going to be your challenge. So I want you to find some suitable assets for your game, and then I want you to create a prefab for your player, a prefab for your first enemy, and I also want you to add a background to your scene. So pause the video now and get that set up. Okay, welcome back. So hopefully you found some assets for your project. And for mine, I'm going to be using some that are available from Kenny. And if you've never heard of Kenny before, then he's a very generous and prolific game developer who offers a lot of assets on his website completely for free. So if we go up to the assets, you'll see that there's a whole bunch here available all under the CC0 license, meaning you can use them for both personal and commercial projects. And the first one I'm going to be looking for on Kenny's website is called Space Shooter Redux. So let's search for Space Shooter, and it's this top one here. And then we can go ahead and download. Now, even though these packs are completely free of charge, if you do have the resources, then do consider donating to Kenny so that he can continue to do this great work of providing free and open source assets for us aspiring game developers. And once that's finished downloading, we'll bring that into our project in Unity. And back over in Unity, I've put mine in its own folder called Asset Packs, and we've got our Space Shooter assets. So in here, if we go into the PNG folder, we're going to need a player ship, and we're also going to look for our first enemy. This is where we're going to run into another problem if we started off in a 3D scene, because if we select one of our sprites, we'll see that the texture type has come in as default. And if you're in a 2D project, which hopefully you are, you'll see that this by default is set to sprite. This means for every image that we ever import into our 3D project that we want to use for 2D, we're going to have to change the texture type in the dropdown to sprite 2D in UI. Then once we've set this, we'll notice a few changes have been made, and then right at the bottom, we're going to have to apply. Now, luckily, we can do a lot of them in one hit, so we can highlight the whole bunch and then change all of them to sprites and apply. Once we've gone and done that, we can then use all of these images as regular sprites like we would do in a regular 2D project. Now back to setting up our player. Let's right click in the hierarchy and create a new empty object called player. Let's reset the transform for now, and then choose one of the available player ships. I'm going to go with this blue one with the nice swept wing, and I'm just going to drag and drop that underneath the player. With our base player set up, let's go ahead and prefab them. So back up in the top level of the assets folder, let's right click and create a folder for our prefabs. And we'll go ahead and drag and drop that into that folder. Next, we're going to want an enemy. So let's right click in our hierarchy, create a new empty game object and reset the transform. Let's call this object enemy0, because we may create more enemies later on, and as programmers, we start counting at 0. Under our enemy, let's find a sprite to attach to them. And I'm going to go with this little red one here. And once again, let's go ahead and drag that into our prefabs folder. Now, if we have a look over on our game screen, we've got both of them occupying the same space at the moment, so we'll move them around in just a moment. But first of all, we want to consider the size of these objects on our game screen. And I think these are just a little bit too big at the moment. So if we click on our main camera, and then in our camera object, let's look at the size. And if we increase the size, we'll notice that we zoom out from our game. And if we decrease the size of our camera, we're going to zoom in. And if you can't see this size option, then just double check that your projection is in orthographic rather than perspective. And that may be a holdover. If you've created a 3D scene, then it usually comes in with a perspective camera instead of an orthographic one. So once we've selected that option from the drop down, I'm going to make the size of this camera projection around about 9. I think that's a reasonable size. The enemies aren't too big on the screen. And then I'm going to go ahead and zoom out a little bit and move my enemy and my player around. So my player is going to start towards the bottom of the screen, maybe around -6. And my enemy is really just there for scale. And they're going to come in, follow a path, and then leave the scene. So player and enemy setup. The last thing we're going to do in this lecture is set up the background image. Now, if we go ahead and look in Kenny's assets, he does have some backgrounds in here, so we could always use one of these. But I've actually gone ahead and created my own, and you'll find a version of this attached to the resources for this lecture. So if we import that image into our project, and I've just dropped mine in the assets pack, we'll go ahead and create an empty object called background. Again, we're going to want to reset the transform, and then just drag our sprite underneath that folder. Now we're getting a little bit of weirdness here because we can see our enemy, but our player seems to have disappeared. And as we found when we were looking at UI, this is because of the layers and the sorting orders. So over in our background starfield image, let's just change the order in layer to -1. This will place it behind our enemy and our player, and so both of them will now appear on top. And later on, when we start getting a bit more complicated with our backgrounds, we'll start looking at this sorting layer as well. But that's good enough for now, and our project is all set up and ready for us to start looking at the new player input system in the next lecture. So I'll see you there. In this lecture, we're going to get our player moving around the screen using the new Unity input system. Okay, so in the last lecture, we imported our Unity input system via the package manager. So go ahead and just make sure that's fully installed and up to date. And then we can go ahead and close our package manager. Now to get the input system working, we need to attach it as a component to a game object. So let's go ahead and find our player in our prefabs folder and then add a new component. The input system can be found under input, or we can go ahead and just search for our player input system. And once we've attached this component, we then need to do a bit of setup. So don't worry too much about all these extra boxes and things. All we need to worry about at the moment is just creating some actions. So let's click on Create Actions, and this will allow us to create a new input action asset. Let's give it a name, and I'm just going to go with input actions for now. Go ahead and hit save. And then up in our root assets folder, we'll have this new input actions. We've also got a warning error coming up down the bottom, but don't worry about that. We can just clear that off when we need to. So let's go ahead and open up our new input actions asset, and this will bring up the asset window. Now there's quite a lot going on in this screen, so let's just break it down one by one. First of all, this is a new asset window, and unlike when we change things in the inspector, if we make changes in here, they won't save automatically. So at the very top, we can see we've got a save asset button in case we change anything. And then over on the right, we have an autosave option. So if you're like me and prone to forgetting that you've changed things in your asset files, then you can always go ahead and enable the autosave. I'm not going to worry about that for now because we're not actually going to be making any changes for the moment. We're just going to have a look around and get a feel for how things work. So the main bulk of this asset window is broken into 3 sections. We have our action maps on the left, our actions in the middle, and then the properties over on the right. So let's start by looking at the action maps. You can see that by default, we've been given a player action map and a UI action map. And all an action map really is just a collection of related behaviors. So under our player, we have the actions of move, look, and fire. And if we look under UI, then we have things like navigate, point, click, submit, and cancel. So you can create new action maps, and this allows you to reuse the same key bindings for different types of gameplay. So you might imagine that in some games you'll have your player action map where you can run around and shoot at things. Then you may have a separate action map for driving or flying or something else. Talking of key bindings, let's next look at the actions section of this screen. And the actions contained within each action map essentially take the button inputs or the physical inputs from a device and ties it to an action that we want to perform in the game. So if we roll down the move action so we can see the actual key bindings themselves, we can see we've got a whole bunch in here. So we've got ones for the gamepads, for the keyboard and mouse and joysticks and things like that. And if we roll down the WASD bindings for move, we can see the specific key bindings where we've got the WA, S and D keys and also the up, down, left and right arrows. And now we've clicked on one of these, let's have a look over at the properties and we can see that our WASD is considered a composite type of a 2D vector. So it'll have an X component and a Y component. And this X and Y component is then further broken down for each key. So the W handles the up part of that composite 2D vector. S controls the down, A is left and D is right. And if we wanted to, we could always change these around to whatever we want. We can also change the key binding itself. So if we didn't want to use D as our down key, we could go ahead and click on this drop down and find an input from this list. Alternatively, if you have the control device plugged in, we can also go ahead and hit listen. And then you just have to press whatever button you want to find that in the input list. So I'm going to keep this as D. So if I press D on the keyboard, we can see that it comes up in our list. Now, like I said, we're not actually going to be changing anything in this input actions asset for now. We will, of course, come back to this later on when we come to start shooting at our enemies, because at that point, we may want to either remap our fire buttons that are automatically assigned or potentially add additional firing actions. I just wanted to give you a brief overview for now so that we can start setting things up in our code. So rather than saving this asset, I'm just going to go ahead and close it down. And then back on our input actions, we've got another piece of setup before we go through this other stuff here. Let's go ahead and drag over the input actions asset into this actions field. And this will open up a whole bunch of new options. And the great thing about this is that if we hover over any of these particular options, we'll get a nice tooltip to explain what it does. For the moment, we're just going to leave everything as default. And the only thing I really want to cover is this behaviors list at the bottom. It's currently on send message and we're actually going to leave it like that. But when you look at Unity documentation, they tend to be written in terms of using the Unity events option. This is a slightly more complicated setup, but it is more flexible and makes full use of the new input system. For now though, while we're just learning about this, let's keep it on send message because that keeps it nice and simple. And in this box below send message, we'll see all of the messages that our input system will be sending out. These can then be intercepted in our code. So let's just have a brief aside and discuss how send messages work. Well, you can think of it like our input system shouting out to any other components that are on the same object that something has happened. So the general chain of command will be that the player presses a button on their keyboard. So imagine they press the W on their keyboard. This is then registered as being the move action from the input system. And the input system will send the message to all the attached components that on move has happened. So to intercept those messages, we're going to need a new script. But before we do that, there's one final piece of setup that we need to do to get our player input working. So if we click on Open Input Settings, and then in the Input Systems Package menu, all we need to do is create our settings asset. This then gets everything set up for us, and we're not going to worry too much about what all these options do for now. So let's just go ahead and close our project settings. And we'll see that we've now got a new scriptable object in our assets folder. With that all set up though, now let's create our new script that will intercept the messages being sent by the player input. So let's add a new component and create a new script called player. And then we can go ahead and open that up. Let's start this script off right by removing our start method because we're not going to need it. And we'll just clear up this note above our update method. And now let's look at how we're going to intercept that onMove message. First of all, we're going to need to go right to the top of the script and add a new using statement. And we're going to be using the Unity engine.input system. Then to intercept that move message, we need a method with the same name. So we can write void onMove. And you can kind of think of this like how the Unity onTriggerEnter functions work and things like that. So Unity will explicitly recognize this method, and we won't have to manually call it from elsewhere in our code. In the parentheses, we're going to need to accept an input value, and we'll just call this the value. And if you remember, our move action was a type of vector2. So we can get our value by saying value.get, and then in chevrons or angle brackets, we can write a vector2. Let's also store this variable for later use. So I'm going to create a vector2 called raw input. And then in onMove, we can just set raw input to our value.getVector2. Now to show how this works, let's go ahead and write a debug.log statement. And we're just going to output the raw input. If we now save our script and jump back over into Unity, let's go ahead and clear our console and hit play. If I press the D key on my keyboard, we'll see that we get a single debug log message. And even though I'm still holding down the key, we're not getting any more messages. However, when I lift my finger off the key, we get another debug log message to say that things have been reset. If I then do the same with the W key, I get a single message, release, and get a reset message. So our onMove method is only being called when we press a key down and when it gets lifted off. This is great for things like button presses and mouse clicks, but we're going to want continuous movement. So when we hold down a key, we continue to move in the given direction. So how do we achieve this continuous movement? Well, if we come out of play and jump back over into our script, this is the reason why I stored our raw input in a separate variable, because we can then use that variable to continuously update our position in the update method. So in our update method, let's create a new vector3 variable called delta, and this is going to store the delta position for our movement, which we can then apply to our transform.position. So for now, let's just set this equal to our raw input, and then we can set our transform.position to plus equals our delta. If we go ahead and save this and jump back into Unity to test it out, I'm going to go back to our scene view and then hit play. And we can now move around, but our movement is incredibly fast because we're moving 1 unit every single frame. And this is going to bring us onto your challenge. I want you to fix our player movement to make it more controllable. Start by adding a move speed variable to our script, and we're going to want to be able to change this in the inspector as well, so keep that in mind. And then I want you to make the movement frame rate independent. We've looked at all of this in previous sections, so pause the video now and give that a go. Okay, welcome back. So hopefully that was some good revision for you and you got on okay with that challenge. So let's start by setting up a movement speed variable. We said we wanted to change this in the inspector, so let's make it a serialized field. And we'll use a float for this and call it the move speed. While we're here, we may as well set it up with a default value. And I think 5 might be a good starting value for this, so let's give that a try. And then down in our update method, let's amend our delta value to be the raw input multiplied by the move speed multiplied by time.delta time. And remember, delta time is the time the last frame took to render. So multiplying by that will just help smooth things out and make our movement frame rate independent. Now, before we go ahead and save our script, the last thing I want to do in here is just to refactor this out of my update method. So I'm going to extract the method by pressing Control and the period key in Visual Studio and extract method. I'm going to get rid of the private declaration because I don't really like it there. I like to keep things tidy. And I'm going to rename my method to move. Now, if we go ahead and save this and jump back over into Unity, let's go ahead and hit play. And we can now move around nicely. Now, we are a little bit slow, so we may want to speed that up later on. But we've got a much bigger problem at the moment in that we can completely leave the game screen and fly wherever we like. So we've done quite a lot of work in this lecture to get our player moving. So we're going to stop things there. And in the next lecture, we're going to look at confining our player to the boundaries of our screen. So I'll see you there. In this lecture, we're going to fix our game so that the player can no longer leave the edges of our screen. Before we do that though, let's jump out of play mode very quickly and just tidy up our assets folder. So I'm going to create a couple of new folders in here. So right click, create folder. And this one is just going to be called the input system. And this is just going to tidy up our input actions and our input system. We're also going to need a folder for our scripts. So let's right click, create folder and call this one the scripts. And then we can drag our player script into that folder. With everything all tidied up, let's head into our scripts folder and open up our player script and look at how we might add these boundaries to the edge of the screen. Now, before we start doing any coding, we're actually going to have to learn a little bit about the viewport and world space. Okay, so what is the viewport? Well, viewport space represents a normalized position relative to our camera. That might seem like complete word salad to a lot of you, so let's bring in a picture of our game so we can relate it to something concrete. In our game, we're already familiar with world space, and these are the positions of our objects in the hierarchy. Viewport space, on the other hand, represents what the camera can see. Specifically, it's the normalized position relative to this camera. So down in the bottom left corner, we start off at position 0, 0. And then as we go around the edges, in the bottom right corner, we have position 1, 0. In the top left, we have position 0, 1. And in the top right, we have position 1, 1. And this is what it means by a normalized position. And to box in our player into what the camera can see, we're going to use a method called viewport to world point. This method converts the normalized position on the screen to a 3D position in world space. So we can use this to find where the edges of the screen are relative to the player in the world. And when we go and do this in code, we're specifically going to be interested in the bottom left and top right corners of the screen, because this will encapsulate our entire viewport. So let's see how to use this method in code by jumping back to our player script. And we're going to need two vector2 variables. The first one is going to be a vector2 called the minimum bounds or the min bounds. And this is going to store that vector2 for the bottom left of the viewport at 0, 0. And then we're going to need another vector2 for our maximum bounds. And that is going to store the value for the top right of that viewport. To initialize these two variables, let's create a new method, and we'll call this a void initBounds. So init is just a shorthand for initialization. Here we're going to need reference to our main camera, and rather than finding it each time we need it, let's create a temporary variable of type camera and call it the main camera. And we'll set this equal to camera.main. So remember that camera.main is the camera in the hierarchy that's tagged with that main camera flag. With the camera found, let's set our minimum bounds. So we'll say minimum bounds equals our main camera.viewport to world point. This method expects a position to be passed into it, and rather than doing a vector3 like it's asking us for, we're actually just going to pass in a vector2 because we don't really care about that z component. And if we use a vector2 instead, then that z component will just automatically default to being 0. So let's pass in a new vector2 at the coordinates of 0, 0, so that bottom left corner of our viewport. Next, we need to follow a very similar process for our maximum bounds. So that is going to be the first of your challenges. I want you to set up the maximum bounds. This is going to be very similar to how we set up the minimum bounds, but we should be using the top right corner for our viewport. So pause the video and give that one a go. Okay, welcome back. So hopefully that wasn't too hard. And in fact, it's so similar to our minimum bounds. I'm just going to copy and paste. I'm then going to rename our variable to maximum bounds because that's the one we're setting. And rather than passing in the bottom left corner of the screen to our viewport to world point method, I'm going to change this from 0, 0 to 1, 1 to be our top right corner. Next, we need to call this initBounds from somewhere. And we really only need to do it once for now. So I know we deleted it in the last lecture, but let's bring back our start method. And in here, we'll call this initBounds method. Next, we need to go ahead and amend our move method to account for these boundaries that we're setting for the player movement. And we're going to do this again with another temporary vector2 variable called new position or new pos. And start with, let's just initialize that as a brand new vector2. This will allow us to then edit the x and the y component of this new vector, and then apply the changes back to the transform.position. So let's start by clamping the x position of our player. So we can say that the new pos.x. And to clamp this variable, we're going to use a method from the mathf class called mathf.clamp. And what this will do is just restrict any values that float outside of the minimum and maximum values that we set. So we can see here that it needs 3 parameters. It needs the value being checked, and it needs the minimum and maximum values that it needs to be checked against. So the value being passed in is going to be our transform.position.x, so the current position of our player, plus the delta.x, so the amount we're going to be moving. And this needs to be kept between our minimum bounds .x and our maximum bounds .x. Next, we need to do a similar thing, but clamping our y position. So this is incredibly similar. So again, I'm just going to copy and paste my code. But this time we're setting our new position.y, and we're clamping our transform position.y plus our delta.y. And we're clamping that between the minimum bounds.y and the maximum bounds.y. Finally, we need to apply this new position, which now includes our delta movement. So at the bottom, we can change our transform.position to equal our new position. And while we're here, we've got a vector3 for our delta position and a vector2 for our new position. And we're generally working with 2D vectors for now. So we can actually go ahead and just change that to a vector2 because we don't really care about that Z component for now. So let's go ahead and save our script and jump back over into Unity to test this all out. To save us waiting around, I'm just going to bump up my move speed for my player just a bit. And now if we move around, we can see that we now get trapped along the edges of our screen. So we can no longer leave the edges. Let's also just check the top, and yep, that all seems to be working as well. But notice that when we hit the edge of the screen, half of our player is still leaving the edge of the screen. And that's because the position of our player is being tracked from its pivot point, which by default is in the middle of our sprite. So we're going to need a way of accounting for that. And the way I'm going to do it is to add some padding around the edge of the screen, similar to how we might add padding to our UI elements. So back over in our player script, let's create some new variables, and these are all going to be serialized fields. So I'm going to need 4 in total, and they're all going to be floats. The first one is going to be called padding left. The second is going to be called padding right. And save the typing. I'm just going to copy this another 2 times. Call the third one padding top. And the last one, padding bottom. The next step is to figure out where we want to apply this padding. There are a couple of options. We could add it to our minimum and maximum bounds, but I'm actually going to add it to where we're calculating our new position. So when we're calculating our new X position and taking into account our minimum and maximum bounds, I'm also going to go ahead and add our padding in here. So in addition to our minimum bounds, we're going to want to add our left padding amount. And for our maximum bounds, we're going to want to subtract our padding right amount. With our X position set, now let's do the same for our Y position. So again, in here, we're going to be adding our padding bottom, and we're going to be subtracting our padding top from the maximum bounds. With that set, let's save our script and jump back into the Unity one more time. Now I've changed our move speed here in the inspector, but I'm actually going to revert that for now and jump over into my player prefab. And now we need to set some values for our padding. If we look up in the transform, the scale of our player is 1, 1, 1. And we know with 0 padding that half of our player goes off the screen. So if we want to keep our player fully in the screen, each of these values is going to have to be 0.5. And I am going to set 0.5 to be my left and right padding for now. But for my top and bottom padding, I'm actually going to change things up a bit, because we're going to want some extra padding at the bottom to account for the UI that we're going to add later on. And we need to make a design decision on whether we want the player to fully explore the top of the screen, or do we want to constrict them to the lower portions. For now, I'm going to say that I don't want my player going right the way to the top of the screen, so I'm going to add a padding of around 5. And for the bottom padding, I'm going to choose a value of around 2. These definitely aren't set in stone though, so let's come out of our prefab and hit play to test this out in our game. So we can now see that we're nicely being constrained on the left side of the screen and nicely constrained on the right of the screen. If we go down, we've probably got just enough space for our UI, so we may want to bring that up a little bit later when we start implementing that. And if we go up, we're getting cut off just around 3/4 of the way up the screen. Again, we may want to change that in the future and bring it down a little bit, maybe to around here. But with our player now set up and able to move around, the next step is going to be to work on our enemies and getting those spawning into the level. We're going to start looking at that in the next lecture, so I'll see you there. Now that we've got our player moving around the screen, it's time to start thinking about adding some enemies. And the way we're going to do this is going to involve a few different scripts talking to each other. So before we just go ahead and start coding things up, let's actually talk about how our enemies are going to work and what scripts we're going to need. Now, our enemies themselves are going to have a few different requirements. They're going to need to be able to cause damage to the player, either through collisions or through shooting at them. And rather than just having a single type of enemy, we're going to have different enemies with different attack behaviors. So they may shoot faster or slower, or they may even have different projectile types. The enemies are going to affect the player's score later on, so if they get destroyed, they're going to increase the player's score. And we may also add a mechanic in there to lower the player's score if they manage to escape unharmed. And the enemies are going to spawn into our game in waves. Now, if you're not familiar with that term, let's have a look at what waves actually are. Well, you can kind of think of them as self-contained moments of gameplay. So we can see an example of a wave here, where we've got 2 enemies following a set path. So for our game, a wave is going to spawn a certain number of enemies over a given amount of time, and all enemies in that wave are going to follow a set path. Once that wave has finished, so either all of the enemies have been destroyed or reached the end of the path, we can then go ahead and generate the next gameplay moment or the next wave. This could be the same as the first, or it could involve different enemies following a different path. So that's the basic mechanics of what we want to happen. But to get all this working, we're going to need a few different scripts working in unison. So next up, let's look at the scripts and their various responsibilities. First of all, we're going to need a wave config file, and this is going to be a scriptable object. This scriptable object is going to tell the wave which enemies need to be spawned. It's going to tell them the path that needs to be followed. And it's also going to control things like the time between enemies arriving within that wave, so they don't all just arrive at the same time. And it's going to control the enemy movement speed. So we may have certain waves where the enemies are quicker or slower. Because all of this is contained within scriptable objects, we're going to need some scripts to actually use this data. And the first is going to be the enemy spawner. This, unsurprisingly, is going to spawn the enemies into our game at the start of the path, but it's also going to dictate the order of the waves. So if we have multiple waves in our game, which we certainly will do, it's going to tell us which one to generate first, and then which one to generate after that one has finished. And finally, it's going to be in control of the time between those waves. So that takes care of bringing the enemies into the world, but we also need to get them moving. This will be the job of an enemy pathfinding script, and all this is going to do is tell the enemy to move to the next waypoint in a path. Now, we're obviously not going to get all of this done in one lecture, so let's just start by getting our enemy moving along a fixed path. And to create a path is actually incredibly simple because we're going to be using a waypoint system. So in our hierarchy, let's right click and create an empty game object and then reset the transform. And we'll call this object path 0 because we very well may have more paths in the future. Then within this empty path object, let's right click again and create another empty object. And we're going to call this waypoint 0. And this time I've placed the 0 in parentheses so that when we duplicate this object, it will automatically index these for us. Before we go ahead and do any duplication though, the general idea is that we're going to have multiple waypoints in this path, and then the enemy is going to move from one to the next. Because these are empty objects, we can't see them in our scene, which makes them very difficult to work with. So to fix this, rather than adding a sprite, which we would see in both our scene and our game view, what we're going to do is head up to the top of our inspector here, where we've got this little cube icon. If we click on that, we then have some icons to choose from. I'm going to pick the yellow diamond so you can see what's going on here. And we can see that in our scene view, we've now got this little yellow diamond. If we zoom in, we can see it a bit better. But if we look over on the game view, that little icon doesn't appear anywhere. So we don't later have to worry about switching these things off in the game view. Now, if we zoom back out so we can see our full game view again here in our scene, let's go ahead now and duplicate some of these waypoints. So just Control D, and I'm going to create 5 in total. All we have to do now is arrange them into a path that we want. I'm going to go with a similar path to what we saw in the slides, but feel free to create whatever kind of path you like. So with my path set up, I've got a nice sweeping curve here. And notice that the start and end points are off of the screen. This is so the enemies can both appear and disappear off camera so that we don't get any abrupt changes where the enemy just pops in or out of existence. With our path set up, let's go ahead and prefab it. And rather than putting it into our prefabs folder, because we're going to have a few of these, let's create a new folder specifically for our waves and our paths. So this will contain all of our paths and all of our wave config data later on. Let's go ahead and drag our path into that folder. And now let's look at how to get our enemy moving. We said the data for things like the path and the enemy movement speed would all be contained within a scriptable object. So let's go ahead and go into our scripts folder and create this scriptable object by right-clicking, going to create and then C# script. And we're going to call this the wave config SO. Now we're not going to write this entire scriptable object in this lecture, but we are going to get enough information in there so that we can move our enemies. This is a scriptable object, so we don't need the start and update method. And we also need to change our mono behavior to be a scriptable object. So that we can create new wave configs in Unity, let's go ahead and add the create asset menu attribute to the top. I'm going to set the menu name to be wave config. And I'm going to give it a default file name of new wave config. Now to get our enemy moving along the path, this scriptable object is going to need 2 variables. These are all going to be serialized fields. And the first is going to be of type transform and is going to be the path prefab that we've just made. So this will contain all of the waypoints that we need. Next, we're going to have another serialized field of type float. And this is going to be the move speed for our enemy. And while we're here, let's give it a default value of around 5. Now, because these variables are private, being that they're in a scriptable object, we're also going to need some getters to access them from outside of this script. And for the move speed, that's going to be fairly straightforward. We're just going to have a public float called getMoveSpeed. And this is just going to return the move speed. But for the waypoints in the path, things are going to get a little bit more complicated because we don't really need the container that those waypoints are in. We want the waypoints themselves. We're also going to want a quick way of grabbing the very first waypoint in the path as well. So let's start off with that one because it's a bit simpler. So our method for this is going to be public and is going to return a transform. And we're going to call this getStartingWaypoint. And the starting waypoint in our path is going to be the very first child of this container. So we can return the path prefab.getChild at index 0. So that will return the very first child for us. Next, we want a way of returning a list of all of the waypoints. So let's create a public method. And this time we're going to return a list of transforms. And we'll call this one getWaypoints. For this, we're going to need to loop through all of the children within our path prefab parent object. And you may be thinking to yourself that a for loop is going to be ideal for this task, and you're certainly not wrong. However, what we're going to do instead of using a for loop is we're going to use a for each loop instead, which works very similarly, but the syntax is slightly different. So how does a for each loop work? Well, first of all, let's remind ourselves of how a for loop works. And in the context of what we're doing, we may have a declaration, something like for int I equals 0. So initializing our iterator at the first index of our path. And then while I is less than the child count of the parent prefab, we want to go ahead and grab the child and then increment our index by 1. And as I said, there's absolutely nothing wrong with doing it this way. However, we could instead opt to use a for each loop, which operates exactly the same but has a slightly cleaner syntax. So to do this exact same thing with a for each loop, we could say for each child transform. So child is a variable in this case, and it's of type transform in our parent. So in our case, our path prefab. Then we want to go ahead and do stuff. So let's head back over to our script. And to return a list of all the waypoints in our path prefab, first of all, we're going to have to create a new list of transforms, and we'll call this waypoints. And then we'll initialize that to be a new list of transforms. Then we're going to go ahead and loop through all of the children of our path prefab. So using our for each syntax, we're going to say for each transform child in path prefab. So we're going to take our path prefab and loop through all of the children and store them as transforms. And every time we do this, we're going to take our waypoints and add the child. Once we've finished doing that and we've gone through all of the children, we can go ahead and return our list of waypoints. So let's save our scriptable object, and that should have everything we need for now. And to stop this lecture from getting too long, we're actually going to stop things there for now, and we're going to write the pathfinding script in the next lecture. So well done for getting our wave config scriptable objects started, and I'll see you in the next lecture where we implement our enemy movement. So I'll see you there. In this lecture, we're going to pick up where we left off last time and create our pathfinding script to get our enemies moving. So let's jump back into Unity and create our next script. Let's right click, create a new C# script called Pathfinder. And then over in our prefabs, let's attach this Pathfinder to our enemy prefab. So we can add our component and find our Pathfinder script. Let's open that Pathfinder script up. And what this script is going to do is set our enemy to the first waypoint in our list, and then iteratively move it towards the next waypoint that it hasn't visited yet. Once it reaches the end of the path and there are no more waypoints in our list, we can go ahead and destroy our enemy. So let's clean up the comments above our start and update to begin with. For our variables, we're going to need reference to a wave config scriptable object. So let's create a serialized field of type wave config so and call this the wave config. And we're also going to want to store the waypoints for our path. So let's create a list of transforms and we'll call it the waypoints. And this will be populated from our scriptable object. Lastly, let's keep track of which waypoint we're currently on. So let's have an integer called waypoint index, and we'll default that to 0 so that it starts at the first waypoint in our list. In start, we want to populate our list of waypoints. So we can say waypoints equals the wave config dot get waypoints. And then we want to move our enemy to the first waypoint in the path. We can do that with transform.position equals the waypoints at waypoint index.position. Then in update, every frame we want to move closer to the next waypoint in the list. So in update, we're going to use a method that we're going to call follow path. And then under update, let's actually create this method. And in here, we want to say that if the waypoint index is less than our waypoints.count, so if we're not at the last waypoint just yet, then we want to move towards the next waypoint in the list. To do this, we're going to need to know where we are, where we're going, and how fast we're moving. Well, we know where we are with our transform.position, so let's think about where we're going and create a vector2 called target position. And we're going to set this equal to waypoints at the waypoint index.position. Next, we want to know how fast we're going. So let's create a float called delta, because this is going to be the distance that we're going to be moving each frame. And we can get that from our wave config .getMoveSpeed. And to make it frame rate independent, we're going to multiply it by time.delta time. To actually move our enemy, we need to set its transform.position for this frame. And for this, we're going to use a method called moveTowards. We can find this method if we type vector2.moveTowards. And we can see from the tooltip here that it requires 3 parameters. It requires the current position, the target position, and the maximum distance delta. And it moves the current point towards the target. So our current position is our transform.position. Our target is going to be our target position, so the position of our next waypoint. And our maximum distance delta is going to be our delta value that we've just calculated. Finally, once we reach the next waypoint in the path, we're going to need to increment our waypoint index. And we can do this by saying that if our transform.position is equal to our target position, then we want to go ahead and take waypoint index and increment it by 1. Now this is giving us a red squiggly error. And if we hover over it, it's saying that it's having trouble checking a vector 3, our position, versus a vector 2, our target position. So let's fix that very quickly, and we can just change our vector 2 here into a vector 3 for our target position. That removes our red squiggly, and our script should now compile. But before we go ahead and test it, there's one more thing we need to add here, and that's what happens when we get to the end of our path. So our if statement will walk us through all of our waypoints, and then if we get to the end, we can say else destroy the game object. So that will remove our enemy from the game once it reaches the end of the path. Now let's go ahead and save our script and jump back into Unity. We've already prefabbed our path, so we can go ahead and delete that from our hierarchy. And then on our enemy, we need a wave config file. So in our waves and paths, let's right click, go up to create, and we should have a wave config file here, which I've incorrectly spelt, so we'll fix that in just a moment. This creates us our new wave config, which let's just call it wave 0 for now. And this needs a path prefab, which we can drag in, and an enemy movement speed, which we can just leave at 5 for now. With our config file set up, let's again go and find our enemy prefab and attach our wave config file. Now, if we go ahead and hit play, we can see that our enemy nicely moves between each waypoint in our path, and when it gets to the end, it gets destroyed. So congratulations on making your enemy move. And now while I go ahead and fix my spelling mistake for my wave config file, I think it's time for your challenge. I want you to go ahead and create at least one new path for the enemies to follow. And then I want you to go ahead and create a new wave config file that uses your new path. So pause the video now and give that a go. Okay, welcome back. So while you've been away, I've gone ahead and created a new path, which is just a mirror image of the path I created earlier. And to create a new wave config file, let's go up and create a new wave config with the correct spelling this time. Let's call this wave 1, and I'm going to attach my new path. Now, if we head back into our scene, we can go ahead and duplicate our enemy for now, attach the new wave that we've just created, and if we hit play, we should see 2 enemies following distinct paths. So everything seems to be working great. And in the next lecture, we're going to expand on what we've done here and start creating those enemy waves. So I'll see you there. We now have our enemies moving along our path and being destroyed at the end, but this only works for enemies that already exist in the hierarchy. So in this lecture, we're going to learn how to instantiate our objects into the scene at runtime. Now this is going to take some modification to our wave config file and our Pathfinder script, and we're also going to be writing a new script for our enemy spawner. Let's start off by going into our wave config file. So let's head into our scripts folder and then open up our wave config SO. Because in here, we're going to want to store all of the enemies that we're going to be instantiating as part of our future waves. So let's create a new variable It's going to be a serialized field, and we're going to use a list of game objects. So we'll have a list of game objects, and we'll call this the enemy prefabs. And the general idea is that we're going to be looping through this list in our enemy spawner and generating or instantiating each enemy in turn. So we're going to need two public getters as well to access the information we need. And we're going to start off nice and early with a challenge. I want you to go ahead and create a getter called getEnemyCount. And this method is going to return the number or count of the enemies in the enemy prefabs list. Our second getter we're going to call getEnemyPrefab, and this is going to pass in an index number. And we want this to return the enemy prefab at the given index in the list. So pause the video now and give that a go. Okay, welcome back. So let's get our methods written. And we're going to start off with our public int getEnemyCount. And all this needs to do is return the enemy prefabs.count. Then for our second getter, this is again going to be public. It's going to return a game object, so the game object in our list. And we're going to call this getEnemyPrefab. We're going to need the index of the game object in our list that we're interested in. So we're going to pass in an int called index. And then to retrieve the item from our list, we can just return the enemy prefabs at the given index. So with that set up, let's save our script. And next we need to create a new script called enemy spawner. So let's pop back into Unity. And then in our scripts folder, let's create a new C# script called enemy spawner. And then open that up. Let's clear off the comment above our start method and get rid of the update method entirely because we're not going to need that at all. And now let's get a reference to our wave config file, which is going to store our enemy list. So let's make this a serialized field of type wave config so and call it the current wave. Then in start, we're going to call a method that we haven't written yet, and we'll call this spawn enemies. Underneath start, let's go ahead and write that method. And this is going to loop through all of the enemies in our wave config file and spawn them into the world. To create objects at runtime, we need to use a method called instantiate. And if we look at the tooltip here, we have 10 different versions of this instantiate method that we can use. And the reason there are so many is because we can do various different things while we go ahead and instantiate our object. So at its bare minimum, we're just going to instantiate the object and not worry about any of the other parameters. And we can do this by taking our current wave .getEnemyPrefab, and then we can pass it in an index. For now, we'll just create the first one in our list, so we'll give it an index of 0. And what this will do in its current state is just create that enemy prefab at runtime at whatever the transform position is of our prefab. However, this isn't quite what we want. We want the enemy to be instantiated at the start of the path. So let's go ahead and add some positional information to our instantiation. And we can see from the tooltip that we're already getting some hints on what to do. Now our starting waypoint is again stored within our wave scriptable object. So we can say current wave .get starting waypoint. This is going to return us a transform, so we can then go ahead and grab the position of that transform. Now this is currently giving us an error because there isn't a version of instantiate that just accepts these two parameters. Whenever we include a position, we're also going to have to include a rotation as well. So to save us going off the end of the page, let's break this up into a few different lines. And we can see here that the rotation needs to be given as a quaternion. Now, don't worry too much about what quaternions are. This is just a certain way of representing rotations that Unity uses behind the scenes. And to specify no rotation, we can say quaternion.identity. We'll notice that with this addition, the red squigglies all disappear. Now, before we go ahead and test this, we've currently got a wave config serialized field in our enemy spawner, and we've also got one in our pathfinder. Now these need to be the same on both scripts, So rather than having them as serialized fields and potentially getting into a state where we've either forgotten to attach one, or we get into a state where we've attached two different wave configs to the different components, let's instead try and link them together. So in our enemy spawner, let's use this version of our wave config and pass it over to the Pathfinder. For this, we're going to need a getter to return the current wave. So let's create a public method that returns a wave config SO called getCurrentWave. And this is going to return our current wave. Then over in our Pathfinder, we can remove this serialized field to make it completely private, but we're going to need reference to our enemy spawner. So let's add a new variable of type enemy spawner, and we'll call this the enemy spawner. Then we need to go ahead and find this object which will exist in our scene. We can do this in the awake method by saying enemy spawner equals find object of type enemy spawner. Then we need to say that our wave config here is going to be the same wave config from our enemy spawner. So down in start, above where we're trying to set our waypoints, because at this point we already need our wave config set up, we can say that our wave config is equal to the enemy spawner dot get current wave. So a fairly minor change in our Pathfinder there, but one that should hopefully help us in the long run. So with all of our scripts saved, let's head back over into Unity. In our hierarchy, let's right click and create a new empty object called the enemy spawner. Let's reset the transform and then add our enemy spawner component. This is going to need the current wave. So in our waves and paths, let's drag over wave 0 for now. And if we go ahead and just look at our enemy, we'll notice that our Pathfinder no longer has that serialized field for the current wave. It's now going to be grabbing that directly from this enemy spawner we've just added. Now over on the waves themselves, so in our scriptable object, we've got this enemy prefabs list. This needs to be populated with some enemies to be spawned. So let's go ahead and head into our prefabs folder and just drag over a single enemy for now. Well, in fact, let's just add a few. Let's add 3 in total. For now, we're only generating the first one in this list and ignoring the others. But in a moment, we're going to look at what happens if we start looping through this list. With that all set up, let's go ahead and delete the 2 enemies that we've got in our scene because we're now going to be generating them at runtime with that instantiation method. To test things, let's hit play. And we now have an enemy being created and then destroyed. Now, if we do that again very quickly and pause, we'll see that the enemy wasn't in the scene before we hit play, but the moment we hit play, this enemy gets generated and it has this clone label at the end, meaning that it's been instantiated at runtime. Now, if we have a lot of enemies being instantiated into our game, then our hierarchy could get fairly messy. So what we could do is store it inside our enemy spawner. This would essentially drag it into here so we could collapse it up, and it doesn't have any real effect on the movement of our objects. So let's see how we can nest it inside our enemy spawner, and while we're there, we'll look at looping through all of the enemies in our list and creating all of them into our game. Back over in our enemy spawner, let's look at nesting our instantiated enemies inside of our enemy spawner. We can also do this within our same instantiate method that we're using here. So if we add another parameter, we can see that it's asking for a transform for the parent. Well, we want the parent to be the enemy spawner itself, so we can just take the transform for this object. And now, when it's instantiated, it will be put inside of our enemy spawner. Next, we want to loop through all of the enemies in our list and create them into the world. And we've done looping several times now using for and for each loops. So have a quick think about which one you think is going to be the most useful in this particular situation. Okay, I'm not going to give you too long. We're actually going to use a for loop for this one. And the reason is that we need the index to be passed in to our enemy prefab. So we're going to have to keep track of how many times we've gone through this loop. So for our loop, we can say for int I equals 0 because we want to start at the first element in our list. We want to loop while I is less than the current wave dot get enemy count, so that's why we included that getter earlier on. And then we want to increment I by 1 every time. Then with our loop set up inside our instantiation, we want to change this 0 to be our iterator I. Now this is going to do the job we've asked of it, but it's not going to work quite how we want it to. To see what we mean, let's save our script and then test it in Unity. And if we hit play and then very quickly hit pause, we can see that our enemies are now contained within our enemy spawner, but also notice that they've all generated at exactly the same moment. And as it stands, they're all directly on top of one another. So we are looping through our list and instantiating all 3 enemies within our config file, but we really don't want them all spawning at exactly the same time and overlapping one another. We really want to space these out so that they appear over time. We've made some fantastic progress so far though with instantiating our enemies runtime, and in the next lecture we're going to look at how to space them out over time. So I'll see you there. In this lecture we're going to get our enemies spawning over time in our waves, and because it's just a small step to get our waves working, we're also going to implement multiple waves. So let's start by heading over to our wave config script, because in here we're going to want to specify the spawn time for each enemy in the wave. So let's create a new serialized field of type float called time between enemy spawns. While we're here, we can give it a default value, so maybe around 1 per second for now. And rather than giving all of the enemies a fixed arrival time, let's add a little bit of variance in there. To do this, we're going to need 2 more variables to keep things working correctly. So we're going to have a float called spawn time variance. And we're going to add or subtract this value from our time between enemy spawns to add that element of randomness. But if you don't want any randomness, we can still use this approach and just set our spawn time variance to 0. And because this is going to be added or subtracted from our time between enemy spawns, if we happen to set a larger variance, which is above the value for our time between spawns, we could end up in some negative numbers. So this is what the third variable is going to control, and this is going to be a float called minimum spawn time. And we can set that to around 0.2 for now. So with those set up, let's create the getter method that's going to return our random spawn time. We scroll all the way down to the bottom and create a public float get random spawn time. First of all, we're going to want to store a random range in a float so that we can return that after we've done some adjustments. So we'll create a temporary variable of type float called spawn time. And this is going to return a random.range between our time between enemy spawns minus our spawn time variance. And if we put the next part on a new line, the maximum value is going to be the time between enemy spawns plus the spawn time variance. Then to cap this lower bound, just in case this goes below our minimum spawn time threshold, we're going to return mathf.clamp. The value we want to clamp is going to be our spawn time. Our minimum value is going to be the minimum spawn time. And for the maximum value, we're going to hold the maximum number that a float can hold. And we can do that with float.maxValue. So with that set up, let's head over to our enemy spawner and actually get our enemies arriving over time. If we head down into our spawn enemies method, we've already written the loop to create the enemies. So we just need a way of delaying this loop for every iteration. And we can do this using something called a coroutine. Now, coroutines are kind of like methods, but they're written and executed slightly differently. The first step to setting up a coroutine is to give our method a new return type. So we're going to change this from void to be an IEnumerator. Now you don't have to worry too much about what an IEnumerator is. You can really just think of this as the method returning something countable that Unity can keep track of. This is giving us a red squiggly error message for our method name, and it's saying that not all code paths return a value. So like a method with a return type, we do need to return something, but unlike a method, we do this in a slightly different way. So inside of our for loop, once we've gone round once, we're going to want to break out of this coroutine and wait for a certain amount of time. And to do this, we're going to need to yield control from our coroutine back to Unity. So our return type for our coroutine is going to be yield return. And then we need to return something. Now, if we wanted this to execute straight away, we could return null. But in our case, we want to wait for a set number of seconds. So we're going to return a new wait for seconds. And we can see in this list here, we've got a few different options. We've got wait until the end of the frame. We've got wait until the end of the fixed update loop. But the one we want is wait for seconds. And the amount of time we want to wait is going to be coming from our wave config. So we can say current wave dot get random spawn time. And this is essentially the coroutine saying that it's done what it needs to do for now and to come back and check on it in a number of seconds. Once that time has elapsed, Unity will check back in on our coroutine and say that you asked me to come back in a number of seconds to see if you had anything else to do. And our coroutine is going to enter the next loop of our for loop, at which point it's going to instantiate our second enemy and then yield control for another amount of seconds. This loop will continue until we've gone through all of the enemies in our list, at which point our coroutine will break out of its for loop and come to a close. So hopefully that logic makes sense, but let's see it in action. And before we can do that, we do need to call a coroutine slightly differently to a method as well. So up in our start method, where we're currently calling a method called spawn enemies, now we need to start a coroutine. And we can do that by writing start coroutine and then placing the method that we want to start in parentheses. So let's save up our script and see this in action in Unity. Before we go ahead and hit play though, let's check on our waves in our waves and paths folder. And if we click on wave 0, which is the one we're currently playing with in the scene, we can see that we've got these 3 new variables. So we've got our time between enemy spawns, which is around a second, and a spawn time variance of 0. To add some randomness, I'm going to set this to around 0.5. So our enemies will now appear between half a second and 1.5 seconds between each other. Now, if we go ahead and hit play, we'll find that our enemies are now nicely spaced out. So adding this coroutine is allowing us to space out the execution of our for loop. The next step of our game is going to be to execute multiple waves. So let's head back over to our enemy spawner script and see how we're going to do this. Well, we're again going to need a couple of new variables. And the first is going to be a list of wave configs. So let's create a serialized field and have a list of wave config SOs. And we'll call this the wave configs. And because we now have all of our wave configs in this list, we don't need to have this current wave serialized anymore. What we're going to do is we're going to populate that based on the current wave from our list. Finally, just like how we have space between our enemies appearing, we may want to have space between our waves appearing. So let's add another serialized field for that. It's going to be a float, and it's going to be the time between waves. And by default, we're not going to have any space at all. So once one wave has generated all of its enemies, we're going to jump straight into the next one. But if you do want to slow that down, then you have some control. If you want even more control, then we can take a similar approach to our enemies from our wave config. But I'm not going to worry about that too much. I'm just going to have a fixed amount of time between each wave. And to loop through all of the waves in our list, we're also going to do that in spawn enemies. But rather than walk you through it step by step, I think it's time for your challenge. I want you to loop through our new list of wave configs. And when you're looping through this list, have a think about whether you can use a for each loop for this, or whether you need a for loop. And to clarify the logic for what we need to do in each loop, we need to set the value for our current wave, because this is going to be very important for our pathfinder. We then want to loop through all of the enemies in that wave, so that's the code we've already got in place. And then after all of the enemies have been spawned for that wave, we want to wait for the time between waves before generating the next one. So pause the video now and give that a go. Okay, welcome back. So let's get our waves working. In our spawn enemies, we need a new loop to go through all of our wave config scriptable objects. And for this, you could use a for loop, but I'm going to use a for each loop because we need to loop through all of them and we don't need to keep track of an iterator like we did for our enemies. So we can say for each wave config SO and we'll call this the wave, in our wave configs list. Then we want to set our current wave equal to the wave that we're currently on for this loop. We then want to take our existing for loop and place that inside of our for each loop. And then after that for loop has completed, we need to yield return, new, wait for seconds, and this time we're going to wait for the time between our waves. Now, before we go ahead and test, rather than calling this spawn enemies, it's now spawning all of our waves and enemies. So to keep our method names descriptive, let's rename it to spawn enemy waves. Save our script and jump back over into Unity. And then on our enemy spawner, we now need to set up our wave configs again. So if we lock the inspector, we can now select multiple things in our project window and drag them over into our list. Let's unlock the inspector so we don't run into problems. Reselect our enemy spawner. And I'm going to set the time between waves to 2 seconds. Now, before we hit play, we've set up our wave 0, but we haven't set up wave 1 yet. So let's go into wave 1 and add some enemies to our list. Let's drag over an enemy into our list and duplicate that a few times. So I'm going to again go with 3 for this wave. And for this one, I don't think I'm going to go with any variants for our spawn time. So let's test this out by hitting play. And we can see our first wave is being generated with some random variants in the enemy arrival. And then once that's finished, the second wave gets generated. If we set our time between waves to 0 and play again, we'll see that the second wave arrives a lot sooner. So even before the first enemy wave has finished traversing the screen. And with that, we have a nice functioning wave system. And at this point, we could go ahead and start creating more waves to add to our list. But regardless of how many we add, we are eventually going to get into a state where these waves come to an end. At which point we may want to transition to a game over or a win screen. Or in my case, I want these to infinitely loop. So once we get to the end of the list, we want to jump back up to the top. That's what we're going to be doing in the next lecture, so I'll see you there. In this lecture, we're going to create an infinite number of waves using a brand new kind of loop. Now, when it comes to creating loops in our code, we've already seen one kind of this, at least in 2 different forms, and that is our for loop. And for loops are great for all kinds of things because they run a set number of times. And we create a for loop with syntax similar to this, so this would loop through all of the children of a game object. Related to our for loop is the for each loop, and this works pretty much the same as a regular for loop, but doesn't track the iterator. So again, we'd have syntax similar to this to loop through all of the children of a game object. So for loops are fantastic, and we've already encountered them many times so far in the course, but there are actually 2 other types of loop that we haven't encountered yet. The first of these is known as a while loop, and a while loop will run continuously, providing some condition that we give it is true. So we might say that while our condition is true, then we're going to run some code. And this is actually very similar to how things like the update method in Unity work. While the game is running, we want to run all of the code in an update loop. Then onto the final type of loop, we've got a do while loop. This is somewhat similar to a while loop, but instead it will always run our code at least once and then continuously repeat the loop while our condition is true. So we might say do some stuff while this condition is true. So while loops are great if we don't know how many times we need to run code, and because we don't specify the number of loops beforehand, we need to be very careful and beware of infinite loops, because they're a very easy trap to fall into, and I myself am notorious for doing this. So whenever we have a while loop, we need to make sure we've got some way of setting its condition to false to allow us to break out of it. So with knowledge of these new kinds of loops, let's jump into our enemy spawner and see if we can't infinitely loop through our list of wave configs. Now, when it comes to deciding where to place our loop within our enemy spawner, we have a couple of options, but I'm going to go with the simplest one and head down to our spawn enemy waves coroutine. Because in here, we can get away with pretty much just wrapping all of our code inside of our loop. But the question still remains, do we want a while loop here or a do while loop? Well, I think we want a do-while loop here, because regardless of whether we want to loop through our list multiple times, we do want to go through it at least once. But rather than just show you how to do this, I think this is going to be your challenge. I want you to go ahead and create a new serialized bool variable at the top of our script called isLooping, and this is going to control the condition for our while loop. Then I want you to create a do-while loop inside of our spawn enemy waves coroutine that will run all of our code once and then repeatedly loop through our wave config list. And to give you a hint for the syntax of this, we want to say do all of our code while the condition is true. And do notice the semicolon there at the end of that while condition. So pause the video now and give that a go. Okay, welcome back. So at the top of our script, we're going to need a new serialized field of type bool. And we said we were going to call this isLooping. And then down in our spawn enemy waves coroutine, we want to say do all of our code here while isLooping. So if we now save our script and jump into Unity, and if we look at our enemy spawner here, we'll see that we've got this isLooping flag. To speed up testing, let's set our time between waves down to 0. And for our first test, we're going to leave this isLooping unchecked. If we go ahead and hit play, we should find that we just loop through the 2 waves in our enemy config list. So there goes our first wave, here comes our second wave, but no third wave is generated. If we come out of play mode, check our isLooping boolean, and then hit play again, this time we should loop through our 2 waves, and then that cycle will continue to repeat. So there's our first wave, here's our second wave, our third wave is coming in, and now we have our fourth wave. So our looping structure seems to be working, and this will continue forever. And if we want to break out of this loop, we just need to set isLooping to false. We're not doing that in code, but we can do it in the inspector. So if we uncheck isLooping here, we'll finish the final loop through all of our wave configs, and then no more waves get generated. So congratulations on creating infinite waves using a do-while loop. And with our wave system pretty much complete now, let's have a look at adding some player health and enemy damage. We'll start looking at that in the next lecture, so I'll see you there. With our enemy waves now working, it's time to start thinking of creative ways to kill our player, because at the moment the enemies can just pass right through them. And I think it would be nice before we start adding things like projectiles is to just have the player take damage if they collide with one of the enemies, so it almost becomes a game of dodge. To do this, we are going to need a couple of new scripts, but before we jump into the code side, let's set up our player and our enemy so that they can interact with each other. Over in our prefabs folder, let's click on both our enemy and our player because we're going to be setting them up pretty much exactly the same. So doing it this way, we can add components to both objects rather than doing them one at a time. Over in our inspector, let's add some components. And the first thing we need is a rigid body 2D. And in here, the only thing we want to change for now is the body type. We want to change it from being dynamic to kinematic. And this is because we're moving all of our objects in code rather than relying on the physics system. With our rigid body added, let's go ahead and add another component. And this time we're going to need a type of collider. Now there are a few different 2D colliders that we can choose from. So you may want to choose a box or a capsule, but I'm actually going to go with a circle. And the reason I've chosen a circle collider here is because I think it will nicely encapsulate our sprites. But depending on the sprites you're using, you may want to choose a different type of 2D collider. With these components added to both our enemy and our player, let's just do some fine adjustments on each. So I'm going to start by going into my enemy prefab and just reducing the size of this circle collider a little bit. And I like to use the edit collider option. So we highlight this and then we can just drag in these nodes to change the size. Now this isn't an exact science and it doesn't have to be perfect, but I think somewhere around here is going to be okay. So if the player collides with the tips of these wings, the collision isn't going to be detected, but it can be nice just to give the player a little bit of leeway so that the game doesn't feel too unfair. Then we're going to do the same thing on our player. So we'll open up our player prefab and again, just change the size of our circle collider. And again, I'm not being too precious about this. So if we happen to clip our wings, we're not going to take any damage, but something around here should be okay. After all, we can always come back and adjust these later on. We're not fixing any of this in stone just yet. And that'll definitely be something we'd want to keep an eye on during our playtesting. So with our collider set up, there is one more thing that I've forgotten to do. So let's select both our enemy and our player once again. And if we go down into our circle collider, we don't want these to be colliders, we want them to be triggers. And this will allow the objects to pass through one another rather than bouncing off each other. So with that all set up, now let's think about what script we're going to need. Well, our player is going to need some health, so we could put that in our existing player script. But since our enemy is also going to need some health, I think it makes much more sense to have a dedicated script purely for looking after the health of an object. So let's create that new script. Let's right click, create C# script and call this the health script. And this is going to be attached to both our player and our enemy. So again, back over in our prefabs, let's select both of our prefabs, scroll down and add the new health component that we've just created. And secondly, we're going to need a way of dealing damage to these objects that have health. So for now, we just want the enemy to be able to hurt the player. But later on, we're also going to want things like projectiles to be dealing damage as well. So again, it makes sense to have a dedicated script that can do this. And this kind of script reuse is really important in game development because it's going to save us a lot of time if we've got a lot of things in our game doing very similar things. So let's create another C# script. And this time we're going to call it the damage dealer. Now to write both of these scripts, let's start off with our damage dealer, because this is going to be an incredibly simple script. It's really not going to do much at all. We're not going to need start and update. And all this is really going to do is hold the amount of damage the object that this is attached to is going to do. So let's create a serialized field of type int and call this the damage value, or just damage in fact. And by default, let's give that a value of around 10. Next, we're going to need a getter so that other scripts can access this amount of damage that needs to be dealt. So we're just going to need a public int get damage and return the damage. Now we may come back and add things to this later on, but at its core, this is really all it needs to do. So let's save our script and now let's go into our health script. This one is going to be a little bit more complicated, but really not by much at the moment. So again, let's get rid of start and update. And this script is going to hold the amount of health our object has. So let's have another serialized field of type int called health. And let's maybe give that a default value of 50. Now the basic logic that we're going to be following is that our damage dealer is going to come in and hit the thing with health and then reduce that health by the damage amount. That's why we went through the trouble of adding those triggers on our objects earlier, so that we can use the onTriggerEnter2D method. So let's write our onTriggerEnter2D method. This requires us to pass in a collider2D, and we'll call this the other collider. And in this method, we want to check whether the thing we're colliding with is a damage dealer. And if it is, we want to take some damage. And there are a few different ways that we might check what the other collider is. We could use things like tags or layer masks and things like that. But what I'm going to do is I'm just going to query whether I can get the damage dealer component off of that other object. So let's create a temporary variable of type damage dealer, and we'll call this the damage dealer. And this is going to be equal to the other.getComponent of type damage dealer. So this will check the collider that we're passing in and see whether we can grab a component of type damage dealer. Now, if this is successful, then our damage dealer variable will hold a reference to that component. But if it fails, our damage dealer is going to be null. So now that we've tried to get our component, we can ask if our damage dealer does not equal null, or in other words, if we do have something stored in that variable, then we want to take some damage And we're also going to want to tell the damage dealer that it actually hit something so that it can destroy itself. So let's start with this second one and tell our damage dealer that it hit something and that it should destroy itself. So over in our damage dealer, let's add another public method. This can be void, and we can just call this hit. In here, we want to destroy our damage dealer, so our enemy that we've hit, or a projectile that's later going to be coming our way. And we can do that with destroy game object. So save our damage dealer, jump back into health, and we can replace our comment here with damage dealer dot hit. With that sorted, now let's think about taking some damage. And this is going to be your challenge. I want you to write the method for taking damage. This method that we're going to call take damage is going to pass in the amount of damage taken, which we can get from our damage dealer, reduce our health by that damage amount, and if we run out of health, then we want to destroy the game object. So pause the video now and give that a go. Okay, welcome back. So let's write our take damage method. We said this wanted to pass in the amount of damage from our damage dealer, so we can get that from our damage dealer dot get damage. So that's us calling the method, but we still need to write it. So underneath our onTrigger enter method, let's have a void take damage. And this is going to pass in an integer for the amount of damage. In here, we want to reduce our health by the damage being taken. So we can say health minus equals the damage. And then if our health runs out from taking this damage, we can say if our health is less than or equal to 0, then we want to destroy our game object. So we're taking a fairly simplistic approach for just destroying objects whenever they hit another object. But later on, we will be expanding on that by adding things like a particle system and explosion sounds and a whole bunch of other cool stuff. But for now, this is good enough. So let's save our script, head over into Unity and test this out. Now, before we go and hit play, we do need to add our damage dealer to our enemy. So in our prefabs folder, let's go to our enemy prefab and add a component of type damage dealer. And our player has been given a default health of 50, the same as our enemy. So let's give our damage dealer for now a value of 25. This will mean we can hit 2 enemies before being destroyed. This is just for testing so we can see things in action. And later on, I'd probably want this to be a lot higher to really incentivize the player not to touch the enemies. But for now, that should be fine. So let's go ahead and hit play and test this out. And now if we collide with an enemy, it disappears. And if we hit a second enemy, then both the player and the enemy get destroyed. So our health and our damage dealing system is working nicely. And with a few tweaks to our enemy wave system to make it more frantic, we could have a very nice game of dodge on our hands. But this is called Laser Defender, and what's a game of Laser Defender without any lasers? So in the next lecture, let's start adding some projectiles for the player to dodge as well, and see how our damage dealer script can be reused for other objects in the game. So I'll see you there. Our game is now coming along nicely. We can dodge the enemies, and if we hit them, we die. But now let's step it up a notch by adding some projectiles, so we can both shoot at the enemies and they can shoot back at us. Before we start coding up this system though, there's a little bit of prep work we need to do beforehand. The first thing we want to do is to create some projectiles that we can instantiate into our world. So over in our hierarchy, let's right click and create a new empty game object and call this the projectile. Let's reset the transform if it didn't come in at 0, 0, 0. And then underneath this object, we're going to add our sprite. We have a whole bunch of sprites in our assets pack folder. So if we dig through into the PNG folder and then into lasers, we have a few options here. We have a whole bunch of blue lasers, green lasers, and red lasers. But because our player is predominantly blue, I'm going to go with one of the blue options. And I quite like the look of this laser blue 07. So I'm going to drag that underneath my projectile. This is pretty small in our game world, so let's scale it up a bit. And I'm going to go with twice the size. So just scale that up to 2 on the X, Y, and Z. And then if we head back to the root of this object, we need to think about some of the components we're going to want to add. Well, this projectile needs to be able to interact with our enemies in the world, so we're going to be setting this up as a trigger collider. This means we're going to need a rigid body 2D, and just like our other objects, let's set that to be kinematic. And we're also going to need a type of collider. Given the shape of our projectile, I think a capsule collider 2D will do the job. And if we zoom in on our projectile, then we can go ahead and edit the collider to fit our projectile. So let's just drag in our handles. And if you're wondering how I'm managing to do both sides at the same time, just need to hold down the Alt key for that. With that looking about right, the last component we want to add is going to be our damage dealer, because our player projectiles are going to need to be able to damage the enemies, and the enemy projectiles, which will be very similar to this, will need to damage our player. Let's leave the default damage at 10 for now. And with all of that set up, we can go ahead and prefab our projectile. So let's just drag that over into our prefabs folder. And I'm actually going to rename this prefab projectile player, because now we're going to create a second one for the enemy. And this really is as simple as duplicating our prefab with Control D, and then let's rename this to projectile enemy. If we open up this projectile, we're going to want to change our laser blue prefab to one that suits our enemies. So let's head back into our asset packs, into the lasers folder. And for this one, I'm going to use the same type of laser, but I'm going to go with the laser red 07. So let's drag that in, delete our blue prefab, and then rescale our red one. And since we duplicated our original projectile, we don't have to worry about setting up all of the colliders and the damage dealer. One thing I am noticing though is that the colliders should be triggers. So let's actually go ahead and just fix that on both of our objects. So is trigger on our enemy projectile. And if we jump into our player projectile, we can set this to a trigger as well. So that's our projectile mostly set up. But if we do leave it like this, we're going to run into a bit of a problem when we start instantiating them via the code. And to show you what I mean, let's go ahead and hit play and then pause very quickly. And if we move our projectile around, so let's zoom out so we can see the full level, and move our projectile out of the way of the enemies. If we unpause our game, our projectile can actually interact and hit our player. This deletes our projectile from the scene and damages our player. And this definitely isn't what we want. We only want the player projectiles to interact with the enemies and the enemy projectiles to interact with the player. So how do we go about doing this? Well, the first step is to set these objects to be on specific layers. So if we click on any object in our scene, we can see up in the top of the inspector that they're all on layer default. If we click on this drop down, and then head to the bottom add layer option, what we're going to do is we're going to set up two new layers. We're going to set up one for the player and one for the enemy. With those two set up, let's click out of our inspector so that that disappears. And now in our prefabs folder, let's select our enemy and our enemy projectile and set both of their layers to be the enemy layer. This will give us a warning message asking whether we want to change the children or just the parent. Let's go ahead and change the children as well. And then we want to do the exact same thing for our player and our player projectile. But this time we're going to set our layer to be the player layer. Again, we can go ahead and change the children. And the reason we want to do this is because we can tell Unity what objects should interact with each other based on their layer. So we can tell the player projectile not to interact with our player ship, and we can tell the enemies not to interact with each other as well. To do this, we need to head up to Edit and then down to Project Settings. And on the left side, we have Physics 2D. Now we also have a physics option as well, which has some very similar stuff in there. But because our project is 2D, we want the Physics 2D option. Then if we scroll to the bottom of this list, we'll find the Layer Collision Matrix. If you can't see that, then just expand this option and then scroll down a little bit. And this collision matrix here tells Unity which layers are allowed to interact with each other. And there's various different reasons why you might want to change things in here depending on the project you're working on. But we said that we didn't want the player projectiles to interact with our player ship and the enemies to interact with each other as well. So in this matrix, we want to say that the enemy can interact with the player, but it can't interact with other enemies. And the player can interact with things on the enemy layer, but it can't interact with other things on the player layer. With those options set, we've also fixed another minor bug that was in our game before. You may or may not have noticed this depending on how you've set up your waves, but after we added our damage dealer and our health system, it turns out that the enemy could collide with another enemy and destroy each other. So this will also fix little problems like that. With that set, let's close our project settings, and now let's test this out to show that it actually works. Let's move our projectile and hit play. And now if we drag our projectile over our player, nothing happens. But if we interact with an enemy, then the projectile gets destroyed and the enemy will take some damage. Next, you may or may not have seen something odd, so let's go ahead and hit play again. And notice that when we move the projectile over the player, the projectile is on top of the player. This looks a bit strange, and we really want the projectile to be instantiated underneath our ships rather than on top of them. So have a very quick think about how you might go about fixing this. Okay, I'm not going to give you too long. What we're going to do is in our projectiles, if we head down to our sprite, we want to make sure that the projectiles are on layer order 0. This should be the case by default, but let's double check both of them. And to make sure that these appear underneath our ships, all we need to do is bump up the ordering layer for our ships. So let's head into our enemy ship and change the layer in order to 1, and then head into our player ship and again change the sprite ordering layer to 1. Now if we hit play one more time, if we zoom in on our player and move our projectile, we'll now see that the projectile appears beneath the player. So when we eventually get around to instantiating this in code in the next lecture, the projectile will appear underneath the player and then shoot out and eventually hit an enemy. So that's our projectile pretty much set up. We can go ahead and delete our prefab from our hierarchy because we're going to instantiate those in code in the next lecture. But before we finish up, there is one more thing that I want to do, and that is to just tweak our input system ever so slightly. So if we head over into the input system folder and open up our input actions, what we're going to do is have a look at the firing action. If you remember, all of this was kind of set up by default when we first added our input system, and we didn't really touch much in here. But if we have a look at our firing action and then expand this drop down to see which buttons and inputs are attached to it, we'll see that we have a left mouse button option, so we can fire when we click the left mouse button. But there's currently no keyboard binding in here. And for our game, I think it would be nice if we had something like the spacebar set up for firing. To do this, all we need to do is click on the plus icon for our fire action, click on Add Binding, and this will add a blank binding to the bottom of our list. Then over in the Properties window, we need to set up the path, which is the key that we're going to be listening for. And we could find it in this list in here. We could dig through our keyboard and find the spacebar. Or we can just hit on listen, press the spacebar, and then it comes up in our list. So let's select our spacebar for our path. And we can also select keyboard and mouse to tell our input actions that this is to be used with the keyboard and mouse control scheme. With that set up, the final change that we want to make is if we click on the fire action again and look over in the properties, we can see that it's got an action type of being a button. And the way this action type is going to work is that when we hit our spacebar to fire, it's going to register the key down event. However, it isn't going to register the key up event. And for our firing action, we're really going to need that key up event so that we can tell the game when to stop firing. So instead, let's change the action type to be of type value. This is the same action type as our move action, and remember that this triggers both when we press the key down and when we lift the key up. So we can now use that information to tell if the key is down and should be firing or not. With our input actions sorted, let's go ahead and save our asset, and do remember to save unless you have the autosave option checked, and then close our asset window. With that set up, we're now in a very good place to start coding up our shooting behavior. And whilst it may seem like we didn't really get too much done in this lecture, we actually set up a lot of groundwork and saved ourselves a lot of potential headaches and bugs going forward. And in the next lecture, we're going to start generating these projectiles at runtime. So I'll see you there. Following all the setup that we did in the last lecture, in this one we're going to get our player shooting. Now, the first step to this is to figure out where we want this shooting behavior to be written. So if we go into our prefabs and have a look at how our player is set up, we're going to be listening for on fire as part of our player input. And if you remember, when we were listening for on move, we were doing that in the player script. So let's have a look at the player script just to remind ourselves of how we were doing that. And if we scroll down, we had this on move event, which was listening for the input itself. So we could also listen for our on fire event in here as well. However, we don't really want the actual shooting behavior to be part of this script because our enemies are also going to need to shoot back at the player. So let's put our on fire method in here to listen for when the player is pressing the fire key. And then later on, we can use this method to set a variable within our shooter script to start that firing process. Before we do that though, I've noticed we've still got a debug log in here for our onMove method. So let's delete that first just to clean things up a little bit. And then underneath this, let's write our onFire method. So just like the one above it, it's going to be void. We're going to call it onFire. And because we changed the action type to be of type value, we can pass in a type of input value called value. And then in here, we're going to be setting a Boolean from our other script. We haven't written that script yet though, so let's save this up for now. And then on our player prefab, let's go down and add a new component called shooter. If we open this up, let's now think about what this script is going to need to do. Well, the way I'm going to do it is I'm going to have this script instantiate some projectiles whenever that fire key is pressed. So to start with, let's clean up our comments, but leave our start and update method alone for now. We're going to need a serialized field to hold the prefab for our projectile. So let's have a game object called projectile prefab. And when we create this projectile, we're going to want it to have a certain amount of speed, and we're going to want it to live for a certain amount of time. So let's control these variables with serialized fields as well. We can have a float called projectile speed. And I think a default value of around 10 should be okay to start with. And we need a serialized field, again of type float, called projectile lifetime. And for this, I think maybe 5 seconds should be okay. Finally, let's actually finish setting up that Boolean flag that we're going to need for our player script. Because this needs to be accessed from another script, let's go ahead and make it public. Our public variable is going to be of type bool, and we're going to call it isFiring. And now with that set up, let's jump back over to our player script and just quickly finish off our onFire method. Before we do that, we're going to need access to our shooter script from within our player script. So right at the very top, let's add a new variable of type shooter, and we'll call it the shooter. And then if we create an awake method to grab that component off of the object, we can say shooter equals get component of type shooter. Now back down in our onFire method, first of all, we can check whether we've got that shooter script. So we can say if shooter does not equal null. In other words, did we find it attached? And if we did, we can set shooter.isFiring to be equal to the value .isPressed. Now that's really all we need to do for our player script. So let's head back over into our shooter script and have a think about how we're going to start instantiating our projectiles. Well, for things like this, I'm quite a big fan of coroutines, and we've seen coroutines once, so this is very good practice to try writing another one. Before we do that, let's set up the framework that this coroutine is going to sit in, because we're going to control the starting and stopping of this coroutine within a fire method. This fire method is going to be checked every update, so let's write a dummy method called fire. And then under this, we're going to write that method, so void fire. And this is where we're going to start that coroutine. And since this coroutine is essentially going to allow us to fire continuously, it would make sense to call this coroutine fire continuously. So finally, let's put the bones of that coroutine in place as well to get rid of our red squiggly. And if you remember, a coroutine has a return type of IEnumerator, and we're going to call this fire continuously. With the bones all set up, we're not going to worry about the red squiggly there for the moment. That's just because we don't have the return type set up yet. But before we go ahead and write that coroutine, let's just think about the logic in our fire method. The way this is going to work is that if our player script tells us that we are currently firing, then we want to start this coroutine. Otherwise, we want to stop our coroutine. To start our coroutine will be nice and simple. We're going to say that if is firing, so that's controlled by that public boolean, then we want to go ahead and start our coroutine. Else, we want to stop our coroutine. Now, how do we stop a coroutine? Well, there are a couple of options depending on how brute force you want to be with it. One option is to just say stop all coroutines. This will indiscriminately stop any coroutine that's running, but it is kind of like taking a hammer to the problem, and we want to be a little bit more surgical. So the other option is to stop coroutine, and then tell it what coroutine to stop. And to tell it which coroutine to stop, what we're actually going to do is when we start our coroutine, we're going to store this as a variable. So this is another really powerful thing that you can do with coroutines. If we head to the top of our class and create a new variable, this variable is going to be of type coroutine, and we're going to call it our firing coroutine. Then we can set this variable by again heading down into fire, and where we're starting our coroutine, we just want to say that our firing coroutine is equal to that started coroutine. Then with that variable set, in our else block, we can stop our firing coroutine. Now, whilst this will do something, it isn't going to be quite what we want. So we will have to come back and adjust our if and our else statement to add some extra information in there. But before we do that, let's go ahead and actually write our coroutine, get some projectiles instantiating into the world, and then we can see the flaws in this current setup and how we might fix it. And writing this coroutine is going to be a challenge for you. I want you to write the logic for our fire continuously coroutine. And this coroutine will loop indefinitely, so think about how to create an infinite loop intentionally. It will instantiate a projectile for every loop around this infinite loop. And we also want to set up the destruction of this instantiated projectile after the projectile lifetime has expired. And as a hint for this one, check out the overloaded versions of the destroy method that we've used before. Finally, we want to wait for the time specified by a variable we're going to call fire rate. And we haven't actually written this variable yet, so go ahead and add this one as well. So quite a big challenge with a lot of moving parts, but pause the video now and give it your very best shot. Okay, welcome back. So the first thing I'm going to do is add our missing variable for our delaying of our coroutine. We're going to set this as a serialized field so we have some control. It's going to be of type float, and we're going to call it the firing rate. And by default, let's set that to maybe around 0.2. Then down in our coroutine, we said we wanted this to loop indefinitely because we are going to be controlling the starting and stopping of our coroutine within our fire method. And to intentionally create an infinite loop, we can say while true. So inside of our infinite loop, we wanted to create a new projectile. And for this, I'm going to instantiate it directly into a temporary variable of type GameObject, and I'll call this the instance. And this is going to be equal to instantiate our projectile prefab. And while I'm here, I'm going to set the position to the transform.position. So it'll be created at the position of the player's ship. And because we've specified a position, we also need to specify a rotation. And we can specify no rotation with quaternion.identity. Now this line is a little long, so let's break it up. Then I said we wanted to destroy this instantiated object after its lifetime had expired. So we can use the destroy method for this. The thing we want to destroy is our instance, and we want to destroy it after the projectile lifetime has expired. Finally, we want to yield our coroutine and wait for the firing rate time to elapse. So we can say yield return. Remember, coroutines always have to yield rather than just return. And we want to return a new wait for seconds of the firing rate. So let's give that a save and jump into Unity to test out what happens. Like I mentioned before, this if-else block isn't quite what we need. So let's have a look at what actually happens in this circumstance before we go and fix it. First of all, let's reopen our player prefab and go down to our shooter script. This needs a projectile prefab, so let's drag in our projectile player. Then if we go ahead and hit play to test this out, we can still move around just fine. We are getting a null reference exception, so we'll look at that in just a moment. And if we try and fire, we get a whole bunch of projectiles all getting spammed out at once, and it's all going a little bit wrong. So let's come out of play mode. And before we fix that dodgy coroutine, let's just have a look at the console log error. And this is giving us a null reference exception saying that the routine is null. Now both of these problems are very easily fixed with our if-else block, so let's have a look at what's happening. What we're doing is when we press the spacebar, we're setting is firing to true. And remember, fire is happening in our update loop, so it's being called every single frame. So when we hit our spacebar, this is set to true, and then every single frame we're starting a new coroutine. The error in the console, on the other hand, comes from our else block. In the time before we hit our spacebar, so right at the beginning of the game, this variable is going to be null. So we're trying to stop a coroutine that hasn't been set. Now, how do we fix both of these problems? Well, the first step is to look at our if statement. What we need to say is that if we are firing and our firing coroutine equals null. So if we haven't set this up already, i.e. we've not called start coroutine yet, then we're going to start firing. Once we've done that once, this statement will be false. So even if we're continuously holding down the fire key, we won't continue to start more coroutines. So that should slow down our firing rate to the correct speed. And for the second one, what we're going to say is else if, because we need to specify some conditions, and we want to specify that we're not currently firing, and our firing coroutine does not equal null. Now this sounds fine in principle, but when we stop a coroutine like this, we're still going to have something in our firing coroutine variable. So to add to our else if block, once we've stopped our coroutine, we're going to set our firing coroutine equal to null. So hopefully the logic checks out there and it all makes sense. Our projectiles aren't moving anywhere though, so let's make that our next priority. And we're going to do this down in our coroutine. If you recall, our projectiles do have a rigid body attached. So what I'm going to do is once we've created the instance of our projectile, we're going to grab that reference to the rigid body, and then we're going to apply a velocity to it. So let's start by grabbing that reference to the rigid body. And so we can do a little bit of extra checking. We're going to store this in a temporary variable of type rigid body 2D, and we'll call this RB. Now we want to go ahead and grab the rigid body component off of our object. So we can say instance.getComponent of type rigid body 2D. And for the extra checking that I was talking about, we're just going to say that if our rigid body RB does not equal null, then we're going to set the rigid body.velocity. And to set our velocity, we need to give it a direction and a speed. Well, for the direction, we can use transform.up. And if we hover over this, it says it's the green axis of the transform in world space. So to explain this in real terms, let's jump back over into Unity and click on our player. And here we can see the green up arrow. So transform.up is going to follow this green arrow. So back in our code, we can take our transform.up, which has a magnitude of 1, and multiply it by our projectile speed. So with that set, let's save that up and jump back into Unity one more time. Let's jump into play mode. And as if by magic, we now have projectiles shooting at our enemies. And if we hit them enough times, then we can destroy our enemies as well. So we've now got a pretty solid game on our hands. If we hit the enemies, then we die. But we now have a way of fighting back and scoring some points. So congratulations on getting the player projectiles working. And in the next lecture, we're going to look at amending our code to get the enemies firing back at the player. So fantastic work, and I'll see you in the next lecture. In this lecture, we're going to get our enemies shooting back at our player. And we're going to do this using the exact same shooter script that we used for our player. Before we go ahead and edit our script though, let's clean up our assets folder by dragging our shooter script into our scripts folder. And then let's head into our prefabs, go into our enemy, and then add our shooter component. In here, we want to give it the projectile prefab. So this time we're going to use our enemy projectile. And for now, we'll just leave all of the other things as default. We can edit those when we start testing. With that set, let's open up our shooter script and see what we need to change to get it to work for our enemies. Well, we want our enemies to fire automatically, so it's really just a case of overriding our isFiring boolean. So this is no longer going to be getting set from a different script. Instead, what we're going to do is we're going to set this to true in our start method. But so this doesn't affect our player as well, let's create a new variable so we can tell the system whether we're using the AI control or the player control. This is as simple as creating a serialized field of type bool that we're going to call useAI. So if useAI is true, we're going to automatically set up our isFiring bool. And if it's false, we're going to accept input from the player. So in start, let's say that if we are using the AI, then isFiring is always going to be true. So let's save up our script as it is and jump into Unity to test this. Inside of our enemy prefab, let's go down to our shooter script and check the use AI option. Now, if we go ahead and hit play, we can now see that our enemies are shooting. But we've got some very weird behavior here. First of all, the shooting is very fast. And secondly, they're shooting in the wrong direction. So let's come out of play mode and fix both these problems. So over on our enemy prefab, let's first of all change our firing rate from 0.2 and make that a bit larger, so maybe around 1, and see how that feels. And to get the projectiles moving in the correct direction, remember that in our shooter script, we were telling it to use the up vector multiplied by the projectile speed. So our enemy is going to be following our up vector, which is still up the screen, even though our sprite makes it look like we're facing down. So first of all, let's rotate our sprite so it follows more closely what the up direction should be. So we'll just jump into our enemy sprite, and on the Z component of our rotation, we'll just change that to 180 degrees. We'll see that the green arrow now points down, but remember this is only for our sprite. So if we click on our enemy, we can see that the up arrow for this is still facing up. With that set, the projectiles will now come out of the front of the ship, but we now need a way of rotating the entire ship so that it faces down the screen. So to do this, we're going to have to rotate our objects when we instantiate them. And if we head over to our scripts folder, this was the job of the enemy spawner. So let's open up our enemy spawner script, head down to where we're instantiating our enemies. And in here, we're setting the rotation to quaternion.identity, so no rotation. But we can very easily change this condition. So instead of using quaternion.identity, we want to rotate our enemy 180 degrees when it's created. There are a few ways to do this, but the easiest way of doing this is to say quaternion.Euler, so E-U-L-E-R. And if you're wondering about the weird spelling versus the pronunciation, it's because it's named after the mathematician Leonhard Euler. Then inside the parentheses, we need to specify the X, Y, and Z rotation. And we don't want to rotate on the X or Y, but we do want to rotate 180 degrees on the Z component. So if we save this and jump back into Unity, and then we can go ahead and hit play, we should now find that our enemies are the right way around and are shooting in the correct direction. So we now have a way of the enemies shooting back at the player. But the projectiles are all on a fixed firing schedule, so it's very predictable gameplay. And this is the next thing that I'm going to want to change. So let's come out of play and head back over into our shooter script one more time. And then let's just recap on our firing coroutine. So while true, we're instantiating our object, giving it some velocity, destroying it after a set amount of time, and then the piece we're interested in is the waiting. So to make this more random, we're going to want to pass a random value into this wait for seconds. And because I think you're up to the task, this is going to be your challenge. I want you to go ahead and modify our coroutine to wait for a random amount of time between our projectiles. And as a hint, why not have a look at our getRandomSpawnTime method from our wave config SO, because the logic here is going to be very, very similar. So once you've had a look at that method that we've written previously, think about what new variables we're going to need to add to our shooter script to make this work, and potentially what we're going to need to change. So pause the video now and give that one a go. Okay, welcome back. So hopefully you got on well with that challenge. And here we are in our wave config SO, so we can see how we did it last time. Well, for our variables, we had a time between enemy spawns, a spawn time variance, and a minimum spawn time. And if we head down to our get random spawn time method, in here we were getting a random spawn time between two values. And then to make sure that we weren't going into negative numbers, we were clamping our result. So let's essentially replicate this same sort of thing in our shooter script. We're currently waiting for our fire rate in our coroutine, but I think this should probably be renamed and used in a slightly different way. So I'm going to rename my firing rate to the base firing rate, and then I'm going to create two more serialized fields. These are both going to be floats, and the first one is going to be called the firing rate variance. And by default, we're going to set this to 0. And then for our second variable, we're going to call this one the minimum firing rate. And we can maybe set that to around 0.1. With those set, let's head down to our coroutine and implement our logic. So in here, we want a temporary variable of type float, which I'm going to call time to next projectile. And this is going to be equal to a random dot range between our base firing rate minus our firing rate variance and our base firing rate plus our firing rate variance. Then to make sure that this value doesn't go below 0, because if it does, we're going to be waiting for negative seconds, which is going to cause us a lot of problems. So we're going to clamp this value by saying time to next projectile is equal to mathf.clamp. The value we want to clamp is our time to next projectile. We want our minimum value to be the minimum firing rate, and our maximum value is going to be our float.max value. And then rather than yielding for the amount of our base firing rate, we want to wait for the time to next projectile. So let's save this up and test it out. Let's head into our prefabs and look at our enemy. We've already set our use AI to be true. We want our base firing rate to be around 1. And we're going to add a variance of maybe around 0.5. So our projectiles will spawn anywhere between half a second and 1.5 seconds between each other. Now, before we actually test, there's one more thing I do want to do in my shooting script, because we're getting a lot of variables in here and it's starting to get very cluttered. We've got this isFiring flag that's public, but we don't ever really need to set it in the inspector, so it would make sense to hide that away. And we've also got a bit of a split between generic shooter functionality and other things specifically related to our AI shooting. So let's jump back into our shooter script for one final time. And if we head up to our variables at the top, we're going to separate this up with some headers. So we can use the header attribute, and I'm going to call the first one general. And this will include our projectile prefab, its speed, lifetime, and maybe our base firing rate as well. And then we're going to have a second header attribute called AI. And this will have our use AI flag and the variables that we're using to modify our firing rate. Finally, we're going to hide away this public variable, and we can do that with another new attribute, and this is called hide in inspector. And just like a serialized field, this doesn't really affect the access level of our variable in code. It only affects the access in the inspector. So let's save this up and jump back into Unity. And now we can see our shooter component is a lot more manageable. If we're just dealing with general stuff, we can set up our first 4 variables. And if we're interested in AI, then we can set these up. And finally, notice that our isShooting variable is no longer present because we've hidden it in the inspector. So with that little bit of cleanup aside, let's finally go and test our game. We now have our enemies shooting at random intervals, which is a lot nicer, and they're shooting a little bit slower, and we can shoot back at them and destroy them. And with that, our core gameplay is pretty much finished. It still requires a little bit of tuning, and we can add some more enemy waves and enemy types, but the fundamentals are all there. However, it is still a little bit boring. So over the next few lectures, we're going to start adding some juice to our game. And the first piece of juice that I want to add is some particle effects to start selling the impact of the projectiles on the enemies. We'll be starting that in the next lecture, so I'll see you there. Our core gameplay is now pretty much there, but our game still feels a little bit dull because our enemies and our player ship just disappear and blink out of existence whenever they get destroyed. So in this lecture, let's add some explosions with some particle effects. Now, whenever I'm working with the particle system, I do like to have some kind of reference to work from, be that from looking at other games or past projects, or even just drawing something down on paper. Now, you don't have to follow exactly what I'm doing in this lecture, so feel free to make this explosion entirely your own. And rather than setting a challenge for this lecture, I encourage you to pause the video frequently to play around with this effect, rather than just copying the numbers that I'm going to be using. Now, the first step to creating our particle system is to add it to the hierarchy. So in our hierarchy, let's right click, go down to Effects, and then add a new particle system. And this currently looks nothing like our end result. And the first biggest thing that I'm noticing is that we're currently spitting out these fuzzy particle balls rather than our nice star-shaped particles. And to change this, we need to look at changing the particle's material. We haven't created this material yet, so let's go ahead and do that first. If we head into our asset packs and then Space Shooter, I've imported this Explosion Stars sprite sheet. If you want to follow along and use the same material as me, then this is attached as a resource to this lecture, so go ahead and download and import that now. Once you've got a sprite sheet that you want to use, the next step is going to be to make it into a material that we can apply to our particles. And we haven't really dealt with materials too much so far. So to create one, let's right click in our assets folder, go up to create and then down to material. Let's call this material M_explosion. And whenever we create a material, it will have a shader which tells Unity how to render it. If we look up in the inspector, we can see under the shader dropdown that these come in as standard by default. But since this is a particle system, we're going to want to change this. So if we click on our drop-down, head down to Particles, and we're going to use the standard unlit shader. Next, we're going to want to change the render mode from opaque down to additive, and that will just make the particles appear correctly when we start using them. And now we need to attach our sprite sheet to this material. So let's grab our sprite sheet and drag it into the little box next to albedo under the maps. Our material is now set up for what we need. So let's now go into our particle system itself, scroll right the way to the bottom under renderer, and we can drag our new material into the materials slot. We can see that this has now changed our particles to be our sprite sheet, but we don't want the entire sprite sheet here. We just want to loop through each individual cell within that sprite sheet. And we can do that with some texture sheet animations. So let's enable our texture sheet animation. And if we open this up, we're going to keep the mode as grid. And for the tiles, we're going to set this to 3 by 1 because our sprite sheet is 3 wide and 1 tall. The changing is quite slow though, so let's bump up our cycles to maybe 2. So this will now loop through the sprite sheet twice. And rather than always starting on exactly the same particle, what I'm going to do is I'm going to select a random one to start with. In the dropdown, let's pick a random between 2 constants and start it anywhere from the first to the third, so between 0 and 2. And now we can see we're getting a little bit more variation. With that set, the next thing I want to do is to amend the colors because they're all white for their entire lifetime and it's not very fiery or explosion-y. So let's go up to color over lifetime and then open up our color picker. And I've actually already got a nice explosion-y type effect that I like to use. But you can go ahead and create whatever kind of explosion you like. You might have purple explosions or green explosions or really anything that you want. To show you how this one is set up, along the top we have various levels of alpha, and this will decrease the alpha over time as it goes through its fire and smoke cycles until eventually petering out entirely. Along the colours we start off with a nice hot yellow colour before we go into oranges, orangey reds, and then we go into a reddish grey colour for our smoke. This is now starting to look a bit more like fire, but it's very much the wrong shape and going in the wrong direction. So let's look at our shape next. It's currently set up to be a cone, but we want it to explode out in a circle. So for our shape, let's click on circle, and this doesn't really do what we want. It's now spreading out on a line. But this is a circle. It's just being rendered in 3D, and the rotation is incorrect. So at the very top of our particle system, let's zero out the rotation, and now we have it generating in a circle. While we're here, let's also zero out the transform, because that really should be zeroed if we're going to prefab this later on. Next, let's try and constrain this explosion so it doesn't spread out quite so far. For this, the first thing I want to do is change the start lifetime. And explosions are quite quick, so let's do a random between two constants and have our particles die out between 0.1 and 0.5. And with that small change, we can now get a better sense of that hot fire from the explosion and then the smoke spreading out. Our particles are all oriented in exactly the same way though, so now let's look at giving it some rotation. So under our start rotation, let's again go with a random between two constants and go from 0 degrees to 359 degrees, so a full circle. And we're also going to come down to rotation over lifetime and give it an angular velocity of around 180 degrees. This allows our particles not only to be instantiated at a random angle, but also gives it some rotation as they travel. So this is looking okay, but it is very sporadic and not very explosion-y yet. So now let's try and amp up the number of particles we've got and really condense them into a quick explosion. Up in our emissions, let's increase the rate over lifetime to say about 100, which is definitely giving us a more sparkly effect. And to tighten up the radius a little bit, let's go down to our shape and change the radius of our circle to maybe around 0.5. This has brought us a good step closer, and the next thing I'm noticing compared to our reference is that our particles are always exactly the same size. So down in size over lifetime, let's enable that. And in our curve, let's flip this line so we start off big and eventually peter out to 0. This has drastically changed the look of our particle system, so we now have a hot fire in the middle and these wispy smoke pieces around the edge. But to get it looking a little bit better, let's change the start speed so all of our particles aren't moving at exactly the same rate. Doing this will allow for a little bit of overlap in our speed and we'll have some bigger pieces of smoke fly out. To start with, let's try a random between two constants and maybe try somewhere between 0 and 2. And again, this has made quite a big difference, but it isn't quite what we want. And this is because when we do a random between two constants, the actual random numbers that get generated are evenly distributed between that upper and lower bound. But we really want more of our particles to be on the quicker end of things. To do this, we can use a curve, so let's select that. And for this curve, I'm going to want a nice ramp between 0 and 2. This means that we'll have more particles being created with a speed closer to 2, and as we head down the curve, we'll end up with less particles at the slower speed. The final step now is going to be to change the duration of our particle system, because if we turn off looping and then restart our particle, it's existing for a very long time and explosions should be very short and sharp. So with looping turned off, let's set our duration down to something nice and snappy, maybe around 0.2. And if we restart our explosion now, we get a nice short sharp explosion. And with that final change, I'm pretty happy with the end result for this particle system for now. It's pretty close to our initial reference, and it looks quite nice. So with that set, let's go ahead and prefab our particle system. And rather than calling it the particle system, let's call this the explosion effect. And we can delete that out of our hierarchy. Next, we want to instantiate this explosion whenever one of the ships is hit. So if we take a look at our scripts and think about where we could do this, the damage is being taken in our health script. So it'd be a good idea to have our health and our particle system linked in some way. Now for this game, we're only going to have the one explosion effect. So I'm actually going to instantiate it directly into this health script. But if you decide to expand on this game later on and add more effects in other parts of your game, then it may be worth creating a brand new script that holds all of these special effects, and then link that to the various scripts that need to call them. So in our health script, let's create a serialized field for our particle system, and we're going to call this the hit effect. And we want to instantiate this particle effect whenever an object takes damage. Now we could place this in our take damage method, but rather than muddying that up, let's create a new method called play hit effect. In here, we're going to say that if our hit effect does not equal null. So if we've attached a hit effect that we want to play, then we want to instantiate that effect. So that we can destroy it later, let's store this in a temporary variable. So for this one, we're going to need a particle system called instance. And then we can go ahead and instantiate our hit effect at the transform.position, so at the position of the thing being hit. And because we've included a position, we need to include a rotation of quaternion.identity for no rotation. Then, to destroy the particles, we can say destroy the instance.gameObject, because the instance is currently just the particle system attached to a game object. And for the duration, we can get the duration of the particle system by saying instance.main.duration. And that will be the duration that the particles are being created. But we also want to include the lifetime of the particles, so we can add the instance.main.startLifetime.constantMax. And you'll see a few different options here, and the one you select depends on how you set up the particle system. So we've got a minimum and a maximum value, but if you've set up a curve, you'll have to worry about animation curves and things like that. For this one though, constantMax will do the job. Finally, we need to call this method from somewhere. So let's take our hit effect, and if we've dealt damage, we're going to take damage, we're going to play our hit effect, and then we're going to tell our damage dealer to process its hit method. So let's save this up and test it out in Unity. Let's first of all link our explosion to both our enemy and our player. So let's click both of those in our asset folder, scroll down to our health script and then drag over our explosion effect. And then we can go ahead and hit play. And our particle systems are now being created. But if we notice, the particles are currently behind our ships. So have a quick think about how we might go and fix this. Okay, I'm not going to give you too long. If we jump into our explosion effect, scroll right down to the bottom where we have our renderer, because this is a problem with the sorting order. If you recall, we're currently working on a rough system of having our projectiles on layer 0, our ships on layer 1. So for our particles, let's change our sort order in layer to 2. If we save our prefab and then test again, we can see that the particles are now appearing on top of our ships. And when ships get destroyed, they go out in a bit more of a blaze of glory. So congratulations on creating your explosion particles. And in the next lecture, we're going to juice our game even more by adding some camera shake when the player gets hit. So I'll see you there.